Hello there and welcome to Cosmos for Sleep. Tonight, we're journeying to the heart of our solar system, exploring the radiant wonders of our sun. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe, let your eyes grow heavy, and let's begin. The Sun contains over 99.8% of the entire solar system's mass, dominating the gravitational landscape with its immense presence, an almost unimaginable concentration of stellar material that profoundly shapes our cosmic neighborhood. This immense and singular presence means it utterly dominates the gravitational landscape of our solar system, acting as the central unwavering anchor. Such an extraordinary mass creates a powerful and pervasive gravitational pull, an invisible yet undeniable force that meticulously orchestrates the graceful, unhurried orbital ballet of all the planets, asteroids, and comets. It holds them securely in their celestial paths, ensuring their steady, predictable journey around our central star with an elegant precision that has unfolded for billions of years. This profound gravitational dominance highlights the Sun's foundational and irreplaceable role in our cosmic home, serving as a vast, radiant source of light, warmth, and stability for everything within its expansive, tranquil reach. Its sheer bulk establishes the fundamental rhythm of our planetary system, a quiet, enduring presence. To truly grasp the Sun's magnificent physical scale, one must contemplate its sheer, overwhelming volume, which is almost beyond human comprehension. Imagine if this colossal, glowing sphere were entirely hollow. A breathtaking 1.3 million Earths could comfortably fit inside its immense fiery interior. This astounding comparison vividly showcases its truly colossal volume, a spherical entity of luminous, superheated gas that effortlessly dwarfs our small blue planet and indeed all other celestial bodies in our cosmic neighborhood combined. It stands as a profound testament to the grand, intricate architecture of our solar system, with the Sun as its undisputed, majestic and central heart, radiating its quiet power and influence across billions of miles of quiescent space. Such an enormous size also means its internal processes are on a scale that defies terrestrial comparison, a true cosmic titan. The radiant light we perceive from the Sun embarks on a swift and constant journey across the vast, tranquil expanse of space, travelling through the silent void between celestial bodies. This luminous voyage takes approximately 8 minutes and 20 seconds to traverse the 93 million miles, or 150 million kilometers, separating its brilliant surface from our waiting planet. This ceaseless stream of photons, the fundamental particles of light, travels at the universe's inherent speed limit, an immutable constant that governs all light and information throughout the cosmos. This subtle, consistent delay in light's arrival is a gentle, everyday reminder of the immense yet comforting distance separating us from our star's life-giving warmth. Each ray of sunlight that softly touches your skin or gently illuminates your surroundings began its luminous voyage just moments before, a tiny, silent messenger traversing the serene, unyielding void, bringing energy and illumination to our world. Deep within its very core, the Sun performs a continuous and profoundly powerful transformation, a process of cosmic alchemy that sustains our entire system. At this innermost heart, it generates an unimaginable amount of energy through a fundamental process known as nuclear fusion. Here, under conditions of immense, crushing pressure and extreme incandescent heat, hydrogen atoms are gently compelled to combine, gracefully transforming into slightly heavier helium atoms. This quiet, persistent and remarkably efficient process is the fundamental, tireless engine that fuels all life on Earth, providing the constant, steady outflow of energy that sustains our delicate ecosystems, warms our atmosphere, drives our climate patterns, and ultimately powers every living thing on our tranquil world. It is the very essential source of our planet's vibrant, flourishing existence, a silent miracle unfolding continuously at the heart of our star, a truly gentle giant. This awe-inspiring fusion process within the Sun is not only continuous, but also remarkably efficient in its cosmic alchemy, a testament to the elegant laws of physics. Every single second, the sun subtly converts an astonishing amount of its own matter into pure energy. Approximately 4 million tons of its mass are transformed into radiant light and heat, a process governed by the elegant and profound principles discovered by modern science. This continuous and staggering release of cosmic power is a profound testament to the intricate and powerful forces perpetually at play within its luminous heart, a wellspring of cosmic energy. It is this gentle, ongoing transformation that allows the sun to shine with such enduring brilliance, steadily illuminating our solar system without pause, a boundless and benevolent cosmic furnace, quietly performing its essential work of creation and sustenance with unparalleled efficiency. Observing the visible surface of the sun, a distinct layer known to astronomers as the photosphere, we witness a vibrant, intensely glowing plasma. This incandescent and dynamic layer is the primary source that radiates the vast majority of the light and heat that travels across the immense distance of space to Earth, making our world habitable. Its average temperature hovers around 10,000 degrees Fahrenheit, which is approximately 5,500 degrees Celsius. From our distant vantage point, it presents as a dynamic, shimmering expanse, appearing to our eyes as a perfectly calm and uniform sea of superheated gas. Yet, beneath this tranquil appearance, it is teeming with subtle underlying activity, characterized by constant convection currents that gently churn and transport energy outward, creating a delicate granular texture visible through telescopes. Venturing further inward, beyond the photosphere and through layers of dense plasma, the sun's true heart holds an even more profound and concentrated warmth. Here, deep within the sun's core, the temperature reaches an astonishing 27 million degrees Fahrenheit, or 15 million degrees Celsius. This makes the sun's innermost region, its very nucleus, the hottest place in our entire solar system. This extreme heat and pressure are precisely what enable the continuous nuclear fusion reactions that define our sun's existence and power, its radiant glow. Our sun is formally classified by astronomers as a G2V yellow dwarf star. This designation places it among a common type of star found throughout our galaxy. Despite the yellow in its classification, when observed from the serene expanse of space, the sun actually appears white. This is because its light spectrum is beautifully balanced, emitting a harmonious blend of all visible colours in roughly equal proportions, which our eyes perceive as pure white light. Earth's atmosphere, however, scatters blue light more effectively, giving our sun its familiar warm, yellowish hue when viewed from our planet's surface. This subtle atmospheric effect creates the comforting golden glow we experience each day, a gentle reminder of our star's balanced cosmic nature. The sun's immense gravity is a fundamental force, profoundly shaping the dynamics of our entire planetary system. Its gravitational pull is an astounding 28 times stronger than Earth's, a powerful, pervasive influence that extends across vast distances. This extraordinary gravitational strength is what holds all the planets, including our own, along with countless asteroids and comets, in their intricate, delicate orbital dance. Each celestial body follows its predestined path, gracefully circling the sun, guided by this invisible tether. Without this immense gravitational anchor, our solar system would simply scatter, losing its coherent structure and the stable, predictable rhythms that have allowed life to flourish on Earth. It is a silent, unwavering force, ensuring the harmonious, unhurried motion of our cosmic family. In terms of its fundamental composition, the Sun is a majestic sphere built predominantly from the lightest elements in the universe. It is composed primarily of hydrogen, which makes up about 73% of its total mass, serving as the essential fuel for its nuclear fusion processes. The next most abundant element is helium, constituting approximately 25% of its mass, the gentle product of its ongoing fusion. The remaining 2% consists of trace amounts of other elements such as oxygen, carbon, neon, and iron. These heavier elements were forged in the hearts of earlier stars that lived and ended their lives long before the Sun's birth. This elemental makeup is a cosmic recipe, providing the perfect conditions for the Sun to sustain its long, luminous life, radiating warmth and light across the solar system with serene consistency. Unlike the solid, rocky planets or the icy gaseous giants, the Sun does not possess a solid surface upon which one could stand. Instead, it is a giant dynamic sphere of superheated plasma. Plasma is often referred to as the fourth state of matter, where atoms have been stripped of their electrons due to extreme temperatures, creating an ionized gas. In this incandescent state, matter behaves with fluid grace, constantly churning and flowing under the influence of intense heat and powerful magnetic fields. This fluid nature means there are no distinct boundaries, only gradual transitions between its different layers, from the dense core to the tenuous outer atmosphere. The Sun's plasma is a vibrant living entity, a continuous shimmering ocean of energy, perpetually in motion, radiating its gentle light and warmth outwards. From this dynamic, plasma-filled expanse, a continuous stream of charged particles flows outward from the Sun, a phenomenon we call the solar wind. This gentle, invisible current of electrons, protons, and other ions travels across the entire solar system, reaching far beyond the orbits of the planets. As it encounters celestial bodies, this solar wind interacts with their magnetic fields, creating beautiful and complex phenomena. On Earth, for example, it is responsible for the captivating auroras, the northern and southern lights, which gracefully illuminate our polar skies. The solar wind, though subtle, is a constant reminder of the Sun's far-reaching influence, extending its ethereal presence and dynamic energy throughout our cosmic neighbourhood, a soft, pervasive breath of our star. On the Sun's visible surface, the photosphere, we sometimes observe darker, cooler regions known as sunspots. These fascinating features indicate areas of intense magnetic activity that subtly suppress the outward flow of heat from the Sun's interior. While still incredibly hot by earthly standards, these regions are cooler than their surroundings, causing them to appear darker to our eyes. Sunspots often appear in groups and can persist for days or even weeks, their presence a quiet indicator of the Sun's ever-changing magnetic landscape. Studying these sunspots allows scientists to gain valuable insights into the Sun's complex internal dynamics and its powerful magnetic fields, which are intricately linked to the broader patterns of solar activity that gently influence our entire solar system. Indeed, the Sun's magnetic field is an incredibly powerful and pervasive force, constantly changing and evolving in a complex rhythmic dance. It extends far beyond the Sun's visible surface, influencing space weather throughout the heliosphere, the vast region of space dominated by the Sun's influence. This dynamic magnetic field creates a myriad of phenomena, from the graceful arches of solar prominences to the more dramatic yet still controlled expulsions of solar flares and coronal mass ejections. Its subtle shifts and reconfigurations drive the 11-year solar cycle, a predictable rhythm of activity that ebbs and flows, creating a dynamic environment that, while powerful, unfolds as part of a majestic natural process. This ever-present, yet invisible, magnetic field orchestrates much of the Sun's elegant activity. The Sun exhibits a fascinating characteristic known as differential rotation, a subtle yet significant aspect of its fluid nature. Unlike a solid body, where all parts rotate at the same rate, the Sun's equator spins noticeably faster than its poles. At the equator, a full rotation takes approximately 25 days, a relatively swift cosmic turn. However, as one moves closer to the poles, the rotation slows, taking about 35 days to complete a full circuit. This graceful, varied rotation is a consequence of the Sun being a fluid sphere of plasma rather than a solid object. This differential motion plays a crucial role in winding and twisting the Sun's powerful magnetic field lines, contributing to the generation of sunspots and other forms of solar activity, a leisurely, complex internal mechanism. Occasionally, the Sun's magnetic field lines can become intricately twisted and then gracefully realign, releasing a sudden, powerful burst of radiation known as a solar flare. These luminous events erupt from the Sun's surface, releasing an immense amount of energy, equivalent to millions of hydrogen bombs, yet they are a natural and integral part of the Sun's life cycle. While powerful, they are not destructive in a chaotic sense, but rather a swift, energetic release. Solar flares emit radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays, sending a wave of energy gently outward into space. These bursts of light and particles are a stunning display of the Sun's dynamic nature, a momentary flash of brilliance in its otherwise steady glow, reminding us of the subtle power held within its luminous form. Building upon the phenomenon of solar flares, the Sun also produces coronal mass ejections, or CMEs, which are vast expulsions of plasma and magnetic field from its outermost atmosphere, the corona. These colossal clouds of charged particles gently drift into space at high speeds, a slow, majestic release of solar material. Unlike the sudden flash of a flare, CMEs are larger-scale events, carrying billions of tons of solar material away from the Sun. When a CME is directed towards Earth, its arrival can interact with our planet's magnetic field, potentially causing geomagnetic storms and enhancing the beautiful auroras. These serene outward movements of solar material are a fundamental part of the Sun's continuous outflow, a grand, unhurried expansion into the vast cosmic sea, showcasing its dynamic and far-reaching influence. From the very heart of the Sun, an astonishing number of nearly invisible particles known as neutrinos are produced every second. These ethereal particles are created during the nuclear fusion reactions deep within the Sun's core. What makes them truly remarkable is their elusive nature. Neutrinos barely interact with matter at all. Billions upon billions of these tiny messengers pass through Earth and even your own body every second, completely unnoticed and without any interaction. They carry direct cosmic information from the Sun's innermost workings, travelling at speeds approaching that of light. Scientists build massive, sensitive detectors, often deep underground, to gently capture these elusive particles, hoping to unlock secrets about the Sun's interior and the fundamental laws of physics. They are silent, ceaseless whispers from the Sun's fiery heart, connecting us to its deepest processes. The energy generated through nuclear fusion in the Sun's core embarks on an incredibly long and patient journey before it finally emerges as sunlight. This radiant energy can take hundreds of thousands of years to travel from the Sun's dense core to its visible surface. It moves not in a direct path, but by slowly diffusing outward through countless collisions and reabsorptions with the dense plasma. Photons, the particles of light, are repeatedly absorbed and re-emitted by atoms, gradually making their way through the radiative zone. This leisurely, meandering process means that the light we perceive today as sunlight began its existence in the Sun's core long before human civilization, undergoing a vast, unhurried trek through the star's interior. It is a testament to the immense scales of time and distance involved in cosmic processes. Our Sun, along with its orbiting family of planets, is not stationary in space. Instead, it is engaged in a magnificent, sprawling journey around the center of the Milky Way galaxy. This grand cosmic orbit is a testament to the vastness of our galaxy and the Sun's place within its intricate design. The Sun completes one full revolution around the galactic center, approximately every 230 million years. This leisurely cosmic journey means that the last time our solar system was in its current galactic position, dinosaurs roamed the Earth. It is an unhurried, graceful dance, carrying us through the galaxy's spiral arms, past countless other stars and nebulae, a slow and steady progression through the vast, star-strewn expanse of our home galaxy. The Sun's behaviour follows a fascinating and predictable rhythm, known as the 11-year solar cycle. This cycle describes a gentle ebb and flow in the Sun's activity, moving from periods of heightened magnetic activity and increased sunspots, known as solar maximum, to quieter periods with fewer sunspots, referred to as solar minimum. This cycle subtly influences space weather throughout our solar system, affecting the intensity of the solar wind and the frequency of solar flares and coronal mass ejections. While these changes can have a gentle impact on Earth's technological systems, they are a natural recurring part of the Sun's majestic life, a consistent cosmic pulse that has been observed and studied for centuries, offering insight into our star's internal dynamics. One of the most breathtaking visual displays of the Sun's influence on Earth is the phenomenon of the dazzling auroras, commonly known as the northern and southern lights. These ethereal, shimmering curtains of green, red, and purple light are created when charged particles from the solar wind gracefully interact with Earth's magnetic field and atmosphere. As these solar particles gently stream towards our planet, they are guided by the magnetic field towards the poles. There, they collide with atoms and molecules in our upper atmosphere, exciting them and causing them to glow. This celestial light show paints the polar skies with serene, dancing colours, a beautiful and visible reminder of the subtle yet profound connection between our sun's outflow and Earth's protective magnetic shield. Beyond its visible surface, the sun possesses an expansive and enigmatic outer atmosphere known as the corona. This ethereal glowing halo is most easily observed during a total solar eclipse, when the moon perfectly blocks the sun's brilliant disk, allowing its delicate structure to become visible. Paradoxically, the corona is dramatically much hotter than the sun's visible surface, the photosphere, with temperatures reaching millions of degrees Celsius. This extreme heat creates a serene mystery for scientists, as it is much hotter than can be explained by the sun's core radiation alone. The corona extends far into space, gradually thinning and transitioning into the solar wind, a vast invisible aura surrounding our star, a beautiful and perplexing region of our sun. The perplexing observation that the sun's outer atmosphere, the corona, is significantly hotter than its visible surface has led to one of the most enduring puzzles in solar physics. Scientists refer to this as the coronal heating problem, a long-standing mystery that continues to engage and challenge researchers. Despite decades of dedicated study and advanced observations, the precise mechanisms responsible for heating the corona to such extreme temperatures remain an active area of investigation. Scientists are diligently working to understand this phenomenon through sophisticated observations from space-based telescopes and intricate computer models. Unraveling this serene mystery promises to deepen our understanding of fundamental stellar processes and the complex interplay of magnetic fields and plasma within our star. From the sun's surface, magnificent structures of glowing plasma often arc gracefully outward, held in place by intricate and powerful magnetic fields. These majestic formations are known as prominences, appearing like fiery rainbows or delicate, glowing ribbons suspended against the darkness of space. They can extend for hundreds of thousands of miles above the sun. Prominences are composed of cooler, denser plasma than the surrounding corona, making them visible as bright features. They are a stunning visual testament to the sun's dynamic magnetic field, which elegantly sculpts and contains these vast quantities of charged gas, creating transient yet breathtaking celestial artistry, a serene and continuous display of magnetic power and plasma. Interestingly, these same gigantic loops of plasma, known as prominences, can take on a very different appearance when viewed against the bright backdrop of the sun's disk itself. In this context, they appear as dark, snake-like structures weaving across the solar surface. When seen this way, they are referred to as filaments, subtly contrasting with the sun's overwhelming brilliance. The darkness of a filament is not due to a lack of light, but rather because the cooler, denser plasma within the prominence absorbs the light from the hotter, brighter photosphere behind it. This optical effect allows scientists to study the structure and dynamics of these magnetic loops from a different perspective, revealing their intricate shapes and movements as they gracefully traverse the sun's luminous face. The visible surface of the sun, the photosphere, presents a fascinating and ever-changing texture. It has a distinctly granular appearance, akin to the gentle bubbling of boiling water or a vast simmering cosmic stew. This intricate pattern is caused by countless convection cells, where hot plasma rises from the sun's interior, cools as it reaches the surface, and then gently sinks back down to be reheated. Each individual granule represents the top of one of these convection cells, creating a dynamic, shimmering mosaic across the sun's face. This constant, unhurried motion of plasma is a fundamental mechanism for transporting energy from the sun's deep interior to its visible surface, a peaceful, continuous churning that fuels its radiant glow. These individual granules, which collectively create the textured appearance of the photosphere, are each remarkably large by terrestrial standards. They measure about 600 miles, or 1,000 kilometers, across roughly the size of a small country on Earth. Each granule is a temporary feature, constantly forming and dissolving as parcels of hot plasma gently rise from below, spread out, cool, and then quietly sink back down to be reheated. This ceaseless cycle of rising and falling plasma occurs over timescales of mere minutes, entire visible surface. This constant, gentle renewal of the granular pattern is a beautiful visual representation of the sun's internal convective processes, a continuous, subtle churning that ensures the steady flow of energy outward. Beyond these smaller, transient granules, the sun's surface also displays larger, less distinct patterns of convection, referred to as supergranulation. These vast, gentle flows of plasma span tens of thousands of miles, encompassing many individual granules within their expansive boundaries. Supergranules are responsible for organizing the sun's magnetic fields on a larger scale, subtly influencing the distribution and behavior of magnetic flux across the solar surface. While not as visually sharp as the smaller granules, their presence is detected through Doppler shifts in the light, revealing the slow, broad movements of plasma. These immense underlying patterns contribute to the sun's overall magnetic architecture, a quiet, pervasive force shaping the larger dynamics of our star. Above the photosphere lies another distinct layer of the sun's atmosphere, the chromosphere. This thin, reddish layer of gas is typically hidden from our view by the photosphere's overwhelming brilliance. However, during the fleeting moments of obscures the sun's disk, the chromosphere becomes beautifully visible. It appears as a delicate ethereal ring of colour, often a soft pink or crimson hue, momentarily gracing the edges of the eclipsed sun. This fleeting glimpse allows scientists to study its unique properties, including its temperature and density, which are distinct from the layers above and below it. The chromosphere is a transitional region, a subtle interface between the visible surface and the much hotter, more expansive corona. The sun's internal structure is a marvel of cosmic engineering, meticulously organized into distinct layers, each playing a crucial role in its overall function. From its very heart, the structure includes the core, where nuclear fusion processes relentlessly generate energy. Surrounding the core is the radiative zone, a vast expanse where energy is transported outward through the gentle, meandering journey of photons. Encasing the radiative zone is the convective zone, where hot plasma rises, cools, and sinks in a continuous boiling motion, carrying energy to the surface. Each of these zones employs distinct physical mechanisms for transporting the sun's immense energy from its fiery birthplace to its outer layers, a highly efficient multi-stage system working in perfect, unhurried harmony. Within the vast expanse of the radiative zone, the method of energy transport is one of patient, slow diffusion. Here, the energy generated in the core travels outward as individual photons, the fundamental particles of light. This journey is not a direct path, but rather a slow, meandering process where photons are repeatedly absorbed and re-emitted by the dense plasma. They bounce from atom to atom over vast distances, taking hundreds of thousands of years to complete their trek. Each collision is a gentle transfer of energy, gradually pushing the heat and light towards the outer layers. It is a patient, unhurried journey through an incredibly dense environment, a testament to the immense timescales involved in the sun's internal processes, a truly cosmic marathon. Beyond the radiative zone lies the convective zone, where the mode of energy transport shifts dramatically to a more dynamic yet still gentle process. In this region, hot plasma rises from deeper within the sun, carrying energy towards the surface. As this plasma reaches the cooler outer parts of the convective zone, it releases its heat, cools, and then gently sinks back down towards the interior to be reheated. This continuous circular motion is similar to the tranquil, bubbling appearance of a vast cosmic lava lamp, or the slow, steady boiling of water in a colossal pot. This convective flow is incredibly efficient at moving energy, creating the granular patterns visible on the sun's surface and ensuring a steady supply of heat and light to its outer layers. One of the most profound aspects of our sun's influence is the existence of its habitable zone, also known as the Goldilocks zone. This is the specific region around a star where conditions are just right for liquid water to exist on the surface of a planet, neither too hot nor too cold. Our Earth is perfectly positioned within this life-sustaining zone, nestled at an ideal distance from the sun. This precise placement ensures that water can remain in its liquid state, a fundamental requirement for the emergence and flourishing of life as we know it. The sun's steady, consistent radiation provides the perfect balance of warmth, allowing our planet to harbour oceans, maintain an atmosphere, and foster the diverse ecosystems that make Earth so uniquely vibrant. A truly humbling thought connects us directly to the distant ancient cosmos. All the heavy elements in your body and on Earth, those beyond hydrogen and helium, were not created in our sun. Instead, they were meticulously forged in the fiery cores of ancient massive stars that lived out their brilliant lives and then gently dispersed their material back into space through spectacular, yet natural stellar deaths long before our Sun was even born. These stellar ancestors enriched the interstellar medium with elements like carbon, oxygen, and iron, the very building blocks of planets, complex chemistry, and ultimately life itself. Our Sun and solar system then formed from this enriched cosmic dust and gas, meaning we are, quite literally, made of stardust. A beautiful and profound legacy of cosmic recycling. Despite its immense mass and central role, the Sun is not entirely stationary in space. Its massive gravitational pull, while dominating the solar system, also experiences a subtle reciprocal influence from the planets orbiting it. This dynamic interplay causes a slight wobble in the Sun's own motion, as it responds to the combined gravitational tugs of its planetary companions. This subtle cosmic dance means the Sun orbits a point slightly offset from its geometric centre, known as the barycenter, which is the centre of mass for the entire solar system. This gentle, rhythmic wobble is a testament to the interconnectedness of all bodies within our solar system, a continuous, elegant gravitational dialogue between our star and its planetary retinue. The amount of solar energy that gently reaches Earth's upper atmosphere per unit area is a precisely measured quantity known as the solar constant. This crucial factor represents the average rate at which the Sun's radiant energy arrives at the top of our atmosphere. While not perfectly constant, as it experiences subtle variations due to the 11-year solar cycle and other factors, it provides a fundamental baseline for understanding our planet's energy input. The solar constant is a crucial factor for Earth's climate and energy balance, influencing atmospheric temperatures, ocean currents, and the distribution of heat across the globe. It is a silent, pervasive measure of the Sun's life-giving power, a fundamental parameter in the delicate cosmic equation that sustains our world. One intriguing puzzle from the Sun's early history is known as the faint young sun paradox. Scientists believe that early in its history, some 4 billion years ago, the Sun was about 30% fainter than it is today, emitting significantly less warmth and light. This poses a profound question. How did early Earth, despite receiving less solar energy, manage to remain warm enough to sustain liquid water and eventually the emergence of life? Various theories propose solutions, suggesting a thicker greenhouse atmosphere or different planetary dynamics in Earth's youth. This paradox highlights the subtle complexities of stellar evolution and planetary climate, reminding us that our star's journey through time has been one of gradual, profound change, a gentle unfolding of its radiant power. Among the most captivating celestial events is a total solar eclipse, a moment of profound cosmic alignment. This rare spectacle occurs when the Moon perfectly positions itself between the Sun and Earth, precisely blocking the Sun's brilliant disk. For a few precious moments, the overwhelming glare of the photosphere is obscured, revealing the Sun's ethereal outer atmosphere, the corona, in all its delicate glory. The corona, usually invisible, shimmers with a pearly white glow, its intricate streamers extending gracefully into space. This captivating sight allows scientists and observers alike to witness the Sun's hidden beauty, a serene and awe-inspiring phenomenon that momentarily transforms our daytime sky into a twilight realm, revealing a celestial crown. A variation of this celestial alignment is an annular solar eclipse, which offers a different, yet equally mesmerizing view of the Sun. This occurs when the Moon passes directly in front of the Sun, but is farther from Earth in its elliptical orbit. Because of this greater distance, the Moon appears slightly smaller in the sky than the Sun's disk. Consequently, it doesn't completely cover the Sun, instead leaving a brilliant glowing ring of sunlight visible around its silhouette. This captivating phenomenon creates a celestial jewel in the sky, a perfect circle of light encircling the dark lunar disk. An annular eclipse is a beautiful reminder of the precise mechanics of orbital motion and the delicate interplay of sizes and distances in our solar system, a subtle cosmic ring. The Sun's vast and powerful magnetic field undergoes a complete reversal of its polarity approximately every 11 years. This regular cosmic rhythm is a fundamental part of the solar cycle, where the Sun's north and south magnetic poles gently swap positions. This process is not a sudden flip, but a gradual transition that occurs during the peak of solar activity, the solar maximum. As the magnetic field weakens and reorganizes, sunspots become more numerous and solar flares more frequent. Once the reversal is complete, the sun settles into the next phase of its cycle. This predictable, gentle cosmic rhythm is a testament to the sun's dynamic internal dynamo, a majestic, recurring transformation that influences conditions throughout the heliosphere. Far beyond the orbits of the outermost planets lies a crucial, distant boundary known as the heliopause. This is the serene edge where the continuous outflow of the sun's solar wind, a stream of charged particles, gracefully meets the interstellar medium, the thin gas and dust that permeates the space between stars. The heliopause marks the outer limit of the sun's direct magnetic and atmospheric influence, forming a protective bubble around our solar system. It is a quiet, invisible frontier, a transitional zone where the sun's gentle breath gives way to the vast, cold embrace of interstellar space, defining the true extent of our star's immediate dominion. This distant boundary is a testament to the sun's far-reaching, yet subtle cosmic presence. In a remarkable feat of human ingenuity and perseverance, both the Voyager 1 and Voyager 2 spacecraft have successfully crossed the heliopause. These intrepid, silent explorers, launched in the 1970s, have ventured beyond the serene edge of our solar system's direct influence and are now drifting through the vast, cold expanse of interstellar space. Their journey represents humanity's first direct contact with the cosmic frontier between our star's domain and the broader galaxy. As they continue their unhurried journey, these spacecraft send back invaluable data, offering unique insights into the properties of the interstellar medium and the delicate interplay between our sun and the wider cosmos. They are distant, quiet witnesses to the sun's far-reaching yet gentle cosmic breath. Deep within the sun's core, the conditions are so extreme that they defy easy human comprehension. The pressure at this innermost region is estimated to be an astonishing 250 billion times greater than Earth's atmospheric pressure at sea level. This unimaginable compression is a direct consequence of the immense weight of the sun's overlying layers, all pulled inward by its own colossal gravity. This crushing pressure is a fundamental ingredient for nuclear fusion, forcing hydrogen nuclei close enough together to overcome their natural repulsion and gently fuse. It is a silent, pervasive force, meticulously maintaining the conditions necessary for the sun to continuously generate the life-giving energy that radiates outward, a testament to the sheer power contained within its heart. Hand in hand with the extreme pressure, the density of the sun's core is equally remarkable, defying common expectations for a gaseous body. Despite being composed entirely of superheated plasma, the density of the sun's core is about 150 times that of water. To put this into perspective, this means a teaspoon of material from the sun's core would weigh approximately 10,000 pounds, or 4,500 kilograms if brought to Earth. This incredible compactness, achieved under immense gravitational forces, is what allows the sun to sustain the nuclear fusion reactions so efficiently. It is a testament to the extraordinary states of matter that exist within stars, a dense, fiery heart that is the engine of our solar system. The sun's primary energy generation process is a fundamental cosmic reaction known as the proton-proton chain reaction. This intricate sequence of nuclear fusion steps is where the sun patiently and gently transforms its vast reservoir of hydrogen into helium. In essence, 4 hydrogen nuclei, which are simply protons, are gradually compelled to fuse together, ultimately forming one helium nucleus. During this subtle transformation, a small amount of mass is converted into an enormous amount of energy, which is then released as light and heat. This continuous, elegant process, unfolding billions of times every second within the sun's core, is the very source of its radiant power, sustaining its long life and providing the essential energy for our entire solar system. To understand the sun's hidden depths and dynamic internal workings, scientists employ a fascinating technique known as helioseismology. This specialized field involves studying the sun's subtle vibrations, much like geologists use seismic waves to probe Earth's interior. By meticulously analyzing the patterns of these gentle, acoustic waves that ripple through the sun, astronomers can infer its internal structure, temperature, density, and even the movement of plasma within its various layers. It's akin to listening to the sun's quiet cosmic song, deciphering the subtle harmonies and rhythms to reveal the unseen processes occurring deep within. Heliosismology provides a unique and powerful window into the Sun's majestic interior, offering insights into its complex, unhurried evolution. The Sun is a prodigious emitter of energy, radiating across a vast and comprehensive range of the electromagnetic spectrum, presenting a complete cosmic symphony of light. From the expansive, long radio waves that journey unimpeded across the cosmos to the intensely energetic yet subtly present X-rays and gamma rays, our star produces an all-encompassing array of radiation. This broad spectrum includes the familiar visible light, which brightens our days and nourishes plant life, as well as numerous invisible forms of radiation, each carrying unique information about the Sun's intricate processes. This rich and varied output allows scientists to meticulously study the Sun using diverse types of telescopes and specialized instruments, each precisely tuned to detect different wavelengths. Through this multi-wavelength observation, researchers are able to reveal the nuanced layers, dynamic events, and subtle transformations occurring within our star, offering a truly harmonious and all-encompassing display of cosmic energy that continually bathes our solar system. Among these various forms of radiation, ultraviolet radiation from the Sun plays a significant and dual role in our daily lives. While it is undeniably essential for certain biological processes, such as vitamin D synthesis, prolonged or excessive exposure to this powerful energy is responsible for the familiar sensation of sunburns and can gently damage skin and eyes if overexposed for extended periods. This makes ultraviolet light a subtle, yet potent reminder of the Sun's immense power, even from its distant vantage point millions of miles away. To safely enjoy its life-giving warmth, wearing protective clothing, sunglasses with appropriate UV filters, and applying sunscreen offers a gentle shield against its more intense rays. Understanding the delicate balance of its ultraviolet output is crucial for both human health and the long-term well-being of our planet's delicate ecosystems, highlighting a nuanced and powerful interaction with a fundamental cosmic force. Complementing the Sun's ultraviolet output, and equally vital, is its infrared radiation, a pervasive form of energy that we primarily experience as warmth and comfort. This indispensable radiation softly warms our planet, meticulously creating the temperate conditions necessary for liquid water to exist in abundance on Earth's surface and for life to flourish across its incredibly diverse environments. From the gentle heat perceived on your skin during a sunny afternoon to the extensive warming of vast oceans and expansive land masses, infrared energy represents a comforting and constant embrace from our distant star. It subtly drives atmospheric circulation patterns, influences the majestic flow of ocean currents, and is absolutely fundamental to Earth's overall energy balance and climate system. This quiet, pervasive heat is an indispensable component of the Sun's life-giving output, ensuring that our world remains a vibrant, hospitable home for countless species, a constant, nurturing presence in the cosmic expanse. While the Sun's radiant energy is predominantly beneficial and sustaining, its powerful solar eruptions can occasionally cause subtle, yet detectable disturbances on Earth. These phenomena are widely known as geomagnetic storms. When particularly strong solar flares or vast coronal mass ejections are directed toward our planet, the charged particles and magnetic fields they carry can gently interact with Earth's protective magnetic field, creating a distant yet significant cosmic ripple. These energetic events can subtly impact satellites orbiting Earth, potentially disrupting their delicate electronic systems and communications. They may also affect power grids and global communication networks here on Earth's surface. While not physically harmful to humans directly, these events serve as a gentle reminder of the intricate interconnectedness of our planet with the dynamic processes of our star, showcasing the Sun's far-reaching yet mostly benign influence across the vastness of space. Within the Sun's enigmatic outer atmosphere, the corona, a fascinating and beautiful phenomenon known as coronal rain, quietly occurs. This refers to parcels of cooler, denser plasma that have condensed from the extremely hot, tenuous coronal gas. Under the subtle yet persistent influence of gravity, and meticulously guided by the Sun's intricate magnetic field lines, this condensed plasma gently falls back toward the Sun's visible surface. It appears as a gentle, fiery descent, often tracing the graceful, arcing paths of the magnetic loops as it flows downward. Coronal rain provides solar scientists with invaluable clues about the complex thermal and magnetic conditions prevailing within the corona, helping them to slowly unravel the long-standing mystery of why this outer atmosphere is so dramatically hotter than the visible surface beneath it. It is a beautiful, subtle dance of plasma, a quiet testament to the sun's dynamic equilibrium and continuous internal adjustments. Another captivating yet fleeting feature of the sun's lower atmosphere are spicules. These are described as thin, bright jets of gas that gracefully shoot upward from the chromosphere, the layer just above the photosphere, into the hotter, more expansive corona. They appear like delicate cosmic fountains, momentarily piercing the boundary between these layers. Each individual spicule is relatively short-lived, typically lasting only a few minutes before gently fading away, only to be promptly replaced by new ones emerging nearby. They are typically about 300 to 600 miles, or 500 to 1,000 kilometers, wide and can extend for thousands of miles into the sun's outer atmospheric layers. Scientists believe spicules play a significant role in transporting both mass and energy into the corona, contributing to its extreme temperature. Their constant, gentle emergence and disappearance create a shimmering dynamic boundary, a continuous subtle interplay of gases and magnetic forces. Often, intricate magnetic loops emerge from the sun's surface, extending far into its atmosphere and connecting different regions of its powerful magnetic field. These majestic loops frequently connect sunspots, serving as invisible conduits that trap and contain vast quantities of hot plasma. As this superheated plasma is held within the confines of these magnetic structures, it creates the magnificent and visually stunning formations we observe as solar prominences. These graceful arches of light into space, appearing as luminous, glowing ribbons against the dark cosmic backdrop. They are a vivid and serene illustration of how the sun's magnetic fields elegantly sculpt and organize its superheated material, forming transient yet breathtaking celestial artistry, a continuous gentle display of magnetic power and plasma suspended in the solar atmosphere. To meticulously study and understand the sun's every subtle change and dynamic behavior, specialized spacecraft are continuously engaged in monitoring our star with unwavering vigilance. Missions such as the Solar and Heliospheric Observatory, widely known as SOHO, and the Solar Dynamics Observatory, or SDO, provide an invaluable, uninterrupted stream of data to scientists worldwide. These advanced observatories capture images and precise measurements across various wavelengths of the electromagnetic spectrum, allowing researchers to accurately track solar flares, coronal mass ejections, the emergence and decay of sunspots, and the intricate evolution of the sun's magnetic field with exceptional precision. Their vigilant observations offer crucial insights into the sun's dynamic behavior, helping us to anticipate space weather events and deepen our understanding of our star's complex, unhurried processes, maintaining a silent, dedicated watchfulness from afar. Pushing the very boundaries of solar exploration, the Parker Solar Probe stands as an intrepid cosmic explorer, meticulously designed to fly closer to the sun than any previous spacecraft in history. Its audacious mission involves venturing directly into the sun's outer corona, a region of extreme temperatures and intense radiation levels. The probe's primary scientific goal is to study the sun's outer corona and to unravel the long-standing mysteries surrounding the origins of the solar wind, gathering unprecedented direct data from within our star's immediate environment. By daring to approach so intimately, the Parker Solar Probe aims to unravel profound questions, such as the coronal heating problem and the precise mechanisms that accelerate the solar wind to such high speeds. It represents a bold yet carefully executed journey into the very heart of our star's influence, a pioneering quest for fundamental cosmic knowledge that promises to transform our understanding. Ultimately, the sun's radiant presence and its continuous boundless energy are absolutely fundamental to photosynthesis, the miraculous and elegant biological process that forms the very base of Earth's intricate food web and sustains virtually all life on our planet. Through the sophisticated mechanism of photosynthesis, plants, various types of algae, and certain bacteria are able to convert sunlight into chemical energy, meticulously transforming carbon dioxide and water into vital glucose, a sugar, and releasing oxygen as a gentle byproduct. This essential biological process not only provides the food and energy for nearly all ecosystems, from the smallest microbes to the largest animals, but also continuously replenishes the oxygen in our atmosphere, making our planet breathable and vibrant. The sun's light is, therefore, not just warmth and illumination, but the ultimate indispensable source of all organic matter and the very breath of life on Earth. A gentle, profound, and cosmic gift that underpins our entire existence and allows our world to thrive. Immense and unwavering gravitational pull is the silent architect of Earth's orbital stability. This pervasive force meticulously keeps our planet in a stable elliptical path at an average distance of about Yamni from its luminous surface. This precise spacing represents a perfect cosmic balance, ensuring that Earth remains within the habitable zone, where temperatures are suitable for liquid water to exist. Without this constant gravitational tether, our world would simply drift aimlessly into the cold, dark depths of space, or be drawn too close to the sun, rendering it uninhabitable. It is a continuous, gentle embrace that safeguards our planet's serene journey around its star, a fundamental aspect of our solar system's enduring harmony, and a testament to the elegant laws of celestial mechanics. One of the most reassuring characteristics of our Sun is its remarkable stability. It is considered a relatively stable star, not prone to rapid, dramatic changes or unpredictable outbursts that could imperil the delicate balance of life on Earth. For billions of years, it has offered a consistent and reliable flow of light and warmth to our solar system, allowing for the gradual evolution and flourishing of complex life forms. While it does exhibit an 11-year cycle of activity, with subtle variations in sunspots and solar flares, these changes are well within predictable bounds and do not fundamentally alter its steady, life-giving output. This enduring consistency provides the foundational environmental stability that has been absolutely crucial for the long-term development of our planet's biosphere, a tranquil and steadfast cosmic companion. To truly appreciate the sun's radiant power, one can consider its sheer brilliance in comparison to other familiar celestial objects. Its light is approximately 157 times brighter than a full moon, illuminating our day with an undeniable and gentle brilliance that utterly transforms our surroundings. While the full moon itself is a beautiful and prominent feature of our night sky, its light is merely reflected sunlight, a pale echo compared to the direct, overwhelming luminosity of its source. This staggering difference in brightness underscores the sun's singular role as the primary illuminator of our world, a constant, pervasive source of energy that defines our concept of day and night and fuels the vibrant activity of our planet, a continuous, unwavering beacon of light. Beyond its natural life-sustaining functions, the sun's abundant energy also presents itself as a clean, inexhaustible, and remarkably renewable source for Earth. Humanity has learned to harness this sustainable cosmic gift through innovative technologies, most notably solar panels. These ingenious devices meticulously convert sunlight directly into electricity, providing a powerful and environmentally gentle means to power homes, businesses, and a vast array of modern technologies. By tapping into this continuous flow of solar energy, we can significantly reduce our reliance on finite fossil fuels, moving towards a more harmonious and sustainable future. The sun's radiant output offers a boundless and benevolent resource, reminding us of the elegant solutions nature provides for our energy needs, a silent, powerful, and ever-present source of cosmic power. The sun's pervasive energy acts as the primary driver for Earth's intricate and dynamic weather patterns, orchestrating a continuous cycle of atmospheric and oceanic activity. Through its gentle warming embrace, the sun heats our planet unevenly, creating temperature differences that give rise to winds, from the softest breezes to the most expansive global air currents. This solar energy also powers the vast ocean currents, which meticulously redistribute heat across the globe, influencing regional climates. Furthermore, it drives the essential water cycle, evaporating water from oceans and land, leading to cloud formation, precipitation, and the replenishment of freshwater resources. Every drop of rain, every gust of wind, and every ocean wave is ultimately a consequence of the sun's radiant power, a testament to its profound and all-encompassing influence on our planet's delicate interconnected systems. Our sun, along with its entire planetary system, is not a static fixture in the universe. but rather a dynamic participant in the grand cosmic dance of the Milky Way galaxy. The Sun is perpetually moving through the vast expanse of our galaxy at an astonishing speed of about 490,000 miles, or 790,000 kilometers, per hour. This constant, unhurried journey carries us along our immense orbit around the galactic centre, a majestic and graceful progression through the star-strewn arms of our home galaxy. Despite this incredible speed, the immense distances between stars mean that our movement feels perfectly serene and imperceptible from Earth. A quiet, continuous voyage through the cosmic ocean, a testament to the grand, unceasing motion of the universe. Over the immense span of its 4.6 billion-year lifetime, the Sun's luminosity, or total energy output, has been steadily and subtly increasing. This gradual increase in its radiant power means that the Sun is slowly becoming brighter and warmer over cosmic timescales. This gentle, yet persistent change has been gradually warming the inner solar system, including Earth. Scientists meticulously track this long-term trend, understanding its implications for planetary climates and the future habitability of our world. This steady evolution of our star is a natural consequence of its ongoing nuclear fusion processes, as its core slowly becomes denser and hotter. It is a slow, patient transformation, a continuous subtle adjustment in its radiant output that shapes the long-term destiny of our cosmic neighbourhood. While the Sun's light appears predominantly white when viewed from the serene expanse of space, its spectrum of light, when analysed scientifically, reveals a subtle peak in the green-yellow range. This means that, technically, the Sun emits slightly more photons in these wavelengths than in others. However, due to the way our human eyes perceive and combine colours, and because all visible wavelengths are present in abundance, the overall impression when looking at unfiltered sunlight is one of pure white. This subtle blend of colours creates the harmonious, balanced light that illuminates our world, a testament to the Sun's stable and consistent energy production across the visible spectrum, a gentle and perfectly balanced cosmic glow. The Sun's rapid rotation, particularly its differential rotation, where the equator spins faster than the poles, creates a subtle yet measurable effect on its overall shape. This dynamic rotation causes a slight oblateness, meaning the Sun is not a perfect sphere. Instead, it is slightly flattened at the poles and exhibits a gentle bulge at its equator. While this effect is far too subtle to be observed with the naked eye, it can be detected with precise scientific instruments. This gentle cosmic shape is a direct consequence of the interplay between its rotational forces and its immense gravitational pull on its fluid plasma body. It is a quiet testament to the physical laws governing rotating celestial bodies, a subtle deformation in its otherwise perfect spherical appearance, a continuous, elegant interplay of forces. Deep within the Sun's core, where nuclear fusion relentlessly occurs, the density of its material is truly extraordinary. It is so incredibly dense that a single teaspoon of its material would weigh an astonishing somehow brought to Earth. This immense concentration of matter is a direct result of the crushing pressure exerted by the overlying layers of the Sun, all pulled inward by its colossal gravity. Despite being a gaseous body, the plasma at its core is compressed to an unimaginable degree, making it incredibly compact. This extreme density is a critical condition for sustaining the proton-proton chain reaction, where hydrogen nuclei are gently forced to fuse into helium, releasing the vast energy that powers our star, a testament to the immense forces at play in its radiant heart. The Sun's powerful magnetic field is a dynamic and ever-changing entity, often displaying intricate patterns of twisting and reconnection. These complex magnetic field lines can become highly tangled and strained by the constant churning of the Sun's plasma. When these stressed magnetic fields gently untangle and reconnect, they release vast amounts of stored energy in phenomena such as solar flares and coronal mass ejections, or CMEs. This process is a dynamic cosmic dance, a continuous rearrangement of magnetic energy that leads to bursts of radiation and expulsions of plasma into space. While these events are energetic, they are a natural part of the Sun's magnetic activity, providing a fascinating glimpse into the interplay between plasma and magnetic forces, a subtle yet powerful cosmic ballet unfolding on our star's surface. Extending far beyond its visible disk, the Sun's atmosphere gradually transitions into a vast invisible aura that permeates our entire solar system. This expansive region, known as the heliosphere, is filled with the solar wind, a continuous flow of charged particles emanating from the Sun. There are no sharp boundaries, but rather a seamless, gentle transition from the dense, hot plasma of the corona to the more diffuse, outward streaming solar wind. This vast, protective bubble of solar material and magnetic fields surrounds all the planets, extending billions of miles into interstellar space. It is a testament to the Sun's pervasive influence, creating a unique environment within our cosmic neighborhood, a serene and continuous outflow that shapes the space around us. Even though it is subtle, the Sun's light pressure contributes to pushing small particles and the ethereal tails of comets away from its radiant surface. As photons, the particles of light, stream outward from the Sun, they exert a tiny amount of force on anything they encounter. While this force is imperceptible on larger objects like planets, it becomes significant for microscopic dust grains and the tenuous gas and dust that make up a comet's tail. This gentle cosmic breeze sculpts the delicate, luminous streamers of comets, always pushing them away from the Sun, regardless of the comet's direction of travel. It is a beautiful demonstration of the fundamental properties of light and its subtle, yet pervasive interaction with matter across the vast, tranquil expanse of space. A constant, gentle push. The Sun's composition serves as a stellar fingerprint, providing invaluable clues about its origins and the cosmic environment from which it emerged. Its precise mixture of hydrogen, helium, and trace amounts of heavier elements reveals that our Sun was born from a cloud of gas and dust that had already been enriched by previous generations of massive stars. These ancient stellar ancestors, through their life cycles and eventual gentle deaths, forged heavier elements in their cores and then dispersed them into the interstellar medium. Our Sun then gravitationally coalesced from this chemically rich material, inheriting the building blocks for planets and life. This composition, therefore, tells a profound story of cosmic recycling and stellar lineage, connecting our Sun directly to the grand evolutionary history of the galaxy, a quiet testament to its cosmic heritage. Looking far into the future, the Sun's eventual transformation into a white dwarf will mark a calm and final stage in its stellar evolution. After gently expanding into a red giant and peacefully shedding its outer layers, its remaining core will contract into a dense, compact object about the size of Earth. This white dwarf remnant will no longer undergo nuclear fusion, but will slowly cool over trillions of years, gradually fading into a dark, dense cinder. This process is not a catastrophic event, but rather a serene and predictable conclusion to its active life, a gentle cosmic transition. It is a testament to the elegant, unhurried life cycle of stars like our Sun, a peaceful descent into cosmic retirement, leaving behind a quiet, luminous jewel that slowly cools into the endless cosmic night. Our Sun, along with its entire solar system, currently resides within a vast, diffuse region of space known as the local bubble. This local bubble is a low-density cavity in the interstellar medium, a region of hot, tenuous gas that was created by ancient supernova events millions of years ago. As these massive stars reached the end of their lives and gently dispersed their material back into the cosmos, they cleared out vast regions of space, leaving behind these expansive bubbles. Our solar system peacefully drifts through this local bubble, a relatively quiet and stable environment within the more turbulent interstellar medium. This cosmic neighborhood provides a serene backdrop for our Sun's journey, a testament to the ongoing, subtle shaping of our galaxy by stellar processes. The sheer scale of the Sun's energy generation is truly astounding, highlighting its role as a boundless cosmic source. Its energy budget is so vast that it radiates more energy in a single second than humanity has consumed throughout its entire recorded history. This continuous, staggering outflow of power underscores the Sun's immense capacity to create and release energy, far surpassing any terrestrial measure. It is a constant, inexhaustible wellspring of light and heat, fueling all life on Earth and driving countless processes across our solar system. This profound abundance of energy is a testament to the efficiency of nuclear fusion, a quiet, continuous miracle unfolding at the heart of our star, reminding us of the vast cosmic forces at play beyond our everyday experience. The Sun's gravitational influence extends far, far beyond the familiar orbits of the planets, reaching into the distant icy fringes of our solar system. This pervasive gravitational pull extends thousands of times farther than the orbit of Pluto, encompassing a vast spherical region known as the Oort cloud. This distant icy realm is thought to be the birthplace of many long-period comets, which remain gravitationally bound to the Sun, patiently waiting in the cold, dark depths. The Sun's subtle yet powerful gravity gently shepherds these icy bodies, occasionally nudging them into the inner solar system, where they can become visible as celestial visitors. This immense reach highlights the true extent of the Sun's dominion, a testament to its colossal mass and its ability to shape the very outer boundaries of our cosmic home. It is difficult to overstate the Sun's essential role in sustaining our planet's delicate ecosystems and indeed, all life on Earth. Without the Sun's constant life-giving light and warmth, our world would be transformed into a frozen, lifeless sphere, shrouded in perpetual darkness and devoid of a liquid water. Photosynthesis, the fundamental process that underpins nearly all food webs, would cease, leading to the collapse of ecosystems. The oceans would freeze solid, and the atmosphere would undergo dramatic changes. The Sun's consistent radiant energy provides the precise conditions necessary for Earth's vibrant biodiversity and complex biological processes to thrive. It is the indispensable heart of our world, a powerful yet gentle cosmic force that continuously breathes life into our planet. The Sun's, a graceful cosmic flip that is a fundamental aspect of its long-term behavior. This occurs because the magnetic poles effectively migrate towards the equator over the course of the solar cycle, gradually weakening as they approach. Once they reach the equator, they then reappear with the opposite polarity at the poles, completing the reversal. This slow, majestic process is driven by the Sun's internal dynamo, the churning of its superheated plasma. This recurring magnetic reorientation influences the frequency of sunspots, solar flares, and coronal mass ejections, creating a predictable yet dynamic rhythm that affects the entire heliosphere. It is a testament to the Sun's complex and powerful magnetic forces unfolding with a serene and consistent regularity. Beyond its role in sustaining ecosystems, the Sun's light is also crucial for producing vitamin D in humans, forming a direct and gentle biological connection between our star and our well-being. When our skin is gently exposed to sunlight, specifically its ultraviolet B rays, it triggers the synthesis of vitamin D, a vital nutrient essential for bone health, immune function, and overall physiological balance. This natural process underscores the profound and intricate ways in which cosmic phenomena subtly influence our very biology. While excessive exposure to sunlight should be avoided, moderate and safe interaction with its rays is an important part of maintaining good health, a constant, subtle reminder of the Sun's life-giving influence on our bodies, connecting us to the radiant energy of our star in a deeply personal way. Beneath the seemingly calm surface of the Sun, the plasma that forms its visible layers is in a state of constant, vigorous motion. This superheated plasma moves at astonishing speeds, reaching hundreds of kilometers per second in a continuous churning motion. This vibrant, fluid environment is driven by the powerful forces of convection, where hot gases rise, cool, and then gently sink back down. This ceaseless internal ballet creates the granular patterns seen on the photosphere and contributes to the Sun's differential rotation. The rapid movement of this ionized gas also generates and shapes the Sun's powerful magnetic fields, which in turn influence the plasma's flow. It is a dynamic and intricate dance of energy and matter, a powerful yet unhurried internal engine that constantly renews the Sun's radiant surface, ensuring its steady glow. The Sun stands as the undisputed titan of our solar system, being the largest and most massive object by a truly significant margin. It accounts for, a testament to its singular dominance, this immense gravitational presence firmly establishes it as the gravitational anchor of our cosmic neighborhood, holding every planet, dwarf planet, asteroid, and comet in its intricate orbital pathways. All other celestial bodies, no matter how large, are but minor components compared to the Sun's overwhelming bulk. This colossal mass ensures the stability and long-term harmony of our planetary system, providing the gravitational foundation upon which our cosmic home is built, a silent, powerful, and central presence that defines our solar system. The journey of energy from the Sun's fiery core to its visible surface is a complex internal ballet, transported through a combination of two distinct yet complementary mechanisms: radiation and convection. In the inner radiative zone, energy gently travels outward as photons, slowly bouncing from atom to atom over hundreds of thousands of years. This patient, meandering journey gradually carries the heat away from the core. Further out, in the convective zone, hot plasma rises, cools, and then sinks in a continuous boiling motion, efficiently carrying the remaining energy to the surface. These two processes work in perfect, unhurried harmony, ensuring a steady and continuous flow of energy that ultimately radiates into space as sunlight. This intricate internal transport system is a marvel of stellar physics, a silent, powerful engine driving our star's luminosity. The Sun's 11-year activity cycle, with its ebb and flow of solar flares and coronal mass ejections, subtly affects the intensity of cosmic rays reaching Earth. During periods of high solar activity, known as solar maximum, the Sun's magnetic field becomes more complex and extends further into space. This enhanced magnetic activity creates a more effective protective shield around our solar system, deflecting some of the high-energy cosmic rays originating from outside the heliosphere. Conversely, during solar minimum, when the Sun's magnetic field is weaker, more cosmic rays are able to penetrate the inner solar system and reach Earth. This dynamic interaction highlights the Sun's role as a cosmic guardian, offering a variable yet vital shield against these energetic particles, a subtle yet significant influence on our space environment. Despite its immense power and presence, the Sun's outermost layers are surprisingly tenuous and diffuse. As one moves away from the visible surface and into the corona, the density of the plasma drops dramatically. In fact, the Sun's outer layers are so tenuous that they are less dense than the best vacuum achievable here on Earth. This subtle and expansive atmosphere extends millions of miles into space, gradually thinning out until it seamlessly transitions into the solar wind. This extremely low density means that while the corona is incredibly hot, it contains very little material. It is a vast, ethereal halo, a testament to the Sun's ability to maintain incredibly high temperatures even in a near vacuum, a silent, pervasive, and surprisingly delicate outer boundary. The Sun's prodigious energy output comes at a subtle, yet continuous cost to its own mass. Due to the fundamental principles of nuclear fusion, where a tiny amount of mass is converted into vast amounts of energy, the Sun's mass is slowly decreasing over time. Every second, approximately 4 million tons of matter are transformed into radiant light and heat, which then streams away into space. This gradual, imperceptible cosmic shedding means that the Sun is slowly yet steadily becoming lighter over billions of years. While this loss is minuscule compared to its overall colossal mass, it is a constant, ongoing process, a testament to the elegant efficiency of its energy generation. This slow, majestic reduction in mass is a fundamental part of its long, unhurried stellar evolution. When we observe the Sun's light, especially through a prism or after a gentle rain shower creating a rainbow, we see a harmonious blend of all the colours of the rainbow. This is because the Sun's light is composed of a full spectrum of visible wavelengths, each corresponding to a different colour. From the deepest violets to the brightest reds, all these hues are present and combine perfectly to appear white to our eyes when viewed directly. This balanced and comprehensive emission across the visible spectrum is what makes sunlight so effective at illuminating our world and driving photosynthesis. It is a beautiful and elegant demonstration of the Sun's pure, unfiltered radiance, a complete and harmonious cosmic blend that brings vibrancy and colour to our planet. The Sun's magnetic field extends far beyond its visible layers, permeating the vast expanse of the heliosphere. This powerful, yet invisible magnetic field forms a protective bubble around our entire solar system. This heliosphere acts as a crucial shield, gently deflecting many of the harmful interstellar particles, such as high-energy cosmic rays that originate from outside our solar system. Without this magnetic bubble, Earth and the other planets would be exposed to a much higher flux of these energetic particles, which could potentially impact our atmospheres and biological systems. It is a silent, pervasive guardian, providing a vital layer of protection for our cosmic home, gentle influence in the interstellar medium. The Sun's rotation axis is tilted by about 7.25 degrees relative to Earth's orbital plane. This subtle cosmic inclination means that the Sun's equator is not perfectly aligned with the plane in which Earth and most other planets orbit. This gentle tilt is a consequence of the complex processes involved in the formation of our solar system, where initial angular momentum and gravitational interactions played a role in setting the rotational axes of both the Sun and the planets. While this tilt is relatively small, it contributes to the overall geometry and dynamics of our solar system, adding a nuanced layer to the celestial mechanics that govern our cosmic home, a subtle, yet persistent, characteristic of our star's orientation in space. Amidst the intense heat of the Sun's visible surface, a surprising phenomenon occurs within its darker, cooler sunspots. Here, the temperature drops just enough to allow for the gentle formation of some complex molecules, a chemical haven amidst the plasma. These fascinating molecular formations, such as titanium oxide and carbon monoxide, would be impossible in the hotter surrounding regions, offering scientists a unique window into the subtle chemistry that can exist even on the surface of a star. It is a testament to the nuanced thermal gradients and powerful magnetic influences that meticulously create these transient cooler pockets, hinting at unexpected complexity in a seemingly simple, fiery environment, a quiet, unexpected chemical crucible within the star's dynamic embrace. This subtle interplay of temperature and magnetic fields reveals a more intricate solar surface than initially perceived, showcasing how even slight variations can lead to remarkable and unexpected chemical processes. The Sun's immense gravitational force, while unseen, is profound enough to subtly warp the very fabric of space-time around it. According to Albert Einstein's groundbreaking theory of general relativity, massive objects like our Sun create a gentle curvature in the cosmic fabric, much like a bowling ball resting on a stretched rubber sheet. This subtle warping dictates the graceful paths of planets, the trajectory of light, and everything else in its vicinity, meticulously explaining the elegant orbits of celestial bodies and the bending of starlight around the Sun. It is an elegant and fundamental aspect of gravity, revealing that space and time are not merely a static backdrop but a dynamic, interwoven entity, gently shaped by the pervasive presence of colossal masses like our Sun, a silent, powerful and ever-present influence on the very geometry of the cosmos. This fundamental understanding of gravity has reshaped our view of the universe. The Sun's radiant energy is the primary driving force behind Earth's vital carbon cycle, a fundamental planetary process that meticulously regulates the continuous flow of carbon between the atmosphere, oceans, and land. Through the miraculous process of photosynthesis, solar energy allows plants to absorb atmospheric carbon dioxide, gently converting it into organic matter. This carbon then moves gracefully through food webs, is stored in vast oceans, and eventually returns to the atmosphere through natural processes like respiration and decomposition. This intricate, continuous cycle is absolutely essential for maintaining Earth's climate stability and supporting the incredible diversity of life on our planet. The Sun's consistent warmth and light provide the necessary energy input, orchestrating this grand planetary exchange with unwavering precision, a gentle, rhythmic breath of our living world that sustains its delicate balance. Far in the distant cosmic future, long after the Sun has transformed into a white dwarf remnant, this stellar jewel will eventually cool into a theoretical, non-radiating cosmic ember known as a black dwarf. This ultimate stage of stellar evolution represents a complete cessation of light and heat emission, as the dense, compact remnant slowly radiates away all its residual thermal energy over an unimaginably long timescale. However, the universe is not yet old enough for any black dwarfs to have formed, as this cooling process is estimated to take trillions of years. It is a concept that stretches our understanding of cosmic time and the ultimate fate of stars like our Sun, a serene, silent end to a luminous existence, a gradual fading into the eternal cosmic night, leaving behind a cold, dense relic. Although completely inaudible to human ears, the Sun generates its own subtle sound waves that continuously ripple through its interior. These acoustic oscillations, which are not sound in the conventional sense of propagating through air, but rather pressure waves moving through plasma, provide invaluable clues about its deep internal structure and precise composition. Scientists use the specialized field of heliosismology to meticulously detect these subtle vibrations on the Sun's surface, interpreting their complex patterns to create detailed maps of its unseen layers, much like an intricate cosmic ultrasound. It is symphony, its radiant heart, offering a unique and powerful window into stellar physics and the dynamic nature of our star. The Sun's powerful ultraviolet radiation, while requiring caution for direct exposure, also plays an absolutely critical and beneficial role in forming Earth's ozone layer. High-energy ultraviolet rays from the Sun gently interact with oxygen molecules in our upper atmosphere, meticulously breaking them apart and then allowing them to recombine into ozone molecules. This ozone layer then acts as a vital protective shield, gracefully absorbing the majority of harmful ultraviolet radiation before it can reach Earth's surface. Without this delicate, naturally formed barrier, life as we know it would be severely impacted by the Sun's more energetic output. It is a profound testament to the Sun's dual nature, both a source of potential harm and an indispensable creator of planetary protection, a continuous, subtle cosmic guardian for our living world, ensuring a habitable environment. The Sun's pervasive gravitational field extends its influence far beyond the familiar to gently influence the orbits of countless comets in the Oort cloud. This vast spherical reservoir of icy bodies, located at the outermost limits of the Sun's gravitational dominion, is where many long-period comets patiently reside, distant celestial wanderers, occasionally nudging them from their quiet repose and sending them on long, graceful trajectories into the inner solar system, where they become visible as celestial visitors, painting luminous arcs across our night sky. It is a testament to the immense reach of our star's gravitational embrace, patiently guiding the most distant members of its cosmic family through the cold, dark expanse. Fundamentally, the Sun's light is a form of electromagnetic radiation, a continuous flow of massless particles called photons. These photons are the universe's primary carriers of energy, traveling through the vast, empty expanse of space at the ultimate cosmic speed limit, the speed of light. From the moment they are created in the Sun's fiery core, they embark on a journey that culminates in connecting us to its distant warmth and illumination. This radiant energy is what powers all life on Earth, illuminates our days, and allows us to perceive the beauty and grandeur of the cosmos. It is a constant, ethereal bridge between our planet and its life-giving star, a silent, pervasive connection that underscores the elegance of physical laws and the profound unity of energy and matter in the universe, an essential cosmic link, even at a significantly greater distance than Earth. The Sun's gentle energy still substantially warms the surface of Mars, allowing for its distinct seasonal changes and influencing its thin atmosphere. While Mars is undeniably a colder, drier planet than Earth, the Sun's radiation still provides enough heat to cause the gentle melting and refreezing of its polar ice caps, and to drive atmospheric circulation patterns that create the famous Martian dust storms. This distant planetary embrace beautifully demonstrates the far-reaching extent of the Sun's thermal influence across our vast solar system. It highlights how our star, though millions of miles away, continues to subtly shape the environments of its planetary companions, a quiet yet profound source of warmth and dynamic activity even on our neighbouring red world, contributing to its geological and atmospheric cycles. In approximately 5 billion years, as the Sun reaches the serene end of its main sequence life, it will undergo a final, beautiful transformation. It will eventually become a planetary nebula, a breathtaking and expanding shell of gas and dust gently expelled from its outer layers. This ethereal cloud, composed of the Sun's former atmosphere, will be illuminated by the brilliant central white dwarf remnant, creating a stunning, colourful display of cosmic artistry visible across vast interstellar distances. This final, serene cosmic display, though fleeting in astronomical terms, will be a majestic farewell, enriching the interstellar medium with heavier elements for future generations of stars and planets. It is a graceful, peaceful conclusion to our Sun's active life, a final burst of radiance before its quiet, long cooling begins, leaving behind a beautiful, glowing monument in the cosmic tapestry. And now, as the gentle future of our Sun unfurls in the cosmic tapestry, the vastness of the cosmos begins to softly recede from your thoughts. You have journeyed through 100 quiet wonders, from the sun's fiery, dense core to its luminous, dynamic surface, and even glimpsed its serene, distant, stellar future. You have drifted through the intricate dance of solar plasma, felt the subtle embrace of its light, and understood its profound influence on our home planet. You are a part of this grand cosmic story, not merely an observer, but a participant woven into the very fabric of stardust and time. The atoms within your body were meticulously forged in the radiant hearts of ancient stars that lived and passed away long before our sun's birth. The air you breathe carries the legacy of distant stellar processes. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through galaxies and drifts in interstellar clouds. Tonight, as you rest and your mind settles, the cosmos continues its quiet unfolding. New stars are forming in distant nebulae. Light is travelling across unimaginable distances, and cosmic dances carry on in silent, elegant harmony. You're a small, warm presence within this vast, radiant sea, peacefully floating among the stars, connected to every shimmering point of light. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.
Hello there and welcome to Cosmos for Sleep. Tonight we're drifting through the radiant lives and quiet deaths of stars, exploring their hidden facts and profound cosmic influence. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy. And let's begin. The carbon in your body, the oxygen you breathe, the iron in your blood, all were forged inside stars. These fundamental elements, essential for life as we know it, did not exist in the early universe. They were created through the immense pressures and temperatures within stellar cores, a process known as nuclear fusion. Every atom heavier than hydrogen and helium in your very being, and indeed in everything around you, began its journey within the heart of a star that lived and died long ago. We are, quite literally, made of stardust, connected to the cosmos in a profound and elemental way. Indeed, this cosmic connection runs deep, as stars truly are the universe's ultimate alchemists, engaging in a continuous process of transformation that underpins all existence. These magnificent celestial bodies function as giant cosmic ovens, tirelessly working to fuse lighter elements into heavier ones within their fiery hearts. From the moment of their luminous birth, stars embark upon a remarkable journey of creation, taking the simplest and most abundant building blocks of the universe, primarily hydrogen and helium, and transforming them into the vast array of elements we encounter throughout the cosmos. This gentle alchemical process is known as nuclear fusion, a quiet, steady force that powers their immense luminosity and sustains their brilliance for billions of years. Deep within a star's incandescent core, under the almost unimaginable pressure and heat that exists there, atomic nuclei are compelled to merge together, forming new, more complex elements. This is the fundamental mechanism through which the universe creates carbon, that versatile element forming the very backbone of all known life, the oxygen that flows through our atmosphere and sustains our breath, the iron within our blood cells, and countless other intricate elements that go on to compose planets, moons, asteroids, and indeed, everything we perceive around us. Without these stellar furnaces, silently operating across the vastness of space, the cosmos would remain a much simpler and far less interesting place, composed almost entirely of the lightest gases, utterly devoid of the rich diversity of matter and the intricate chemical structures we observe and experience today. The quiet hum of fusion within each star is a continuous and profound act of cosmic manufacturing, steadily building the intricate chemical tapestry of existence, piece by gentle piece, over unimaginable spans of time. It is a testament to the universe's capacity for self-creation, a quiet internal forging of the raw materials for all future wonders, forming the very essence of what we are. Long before stars like our familiar sun began to grace the night sky with their comforting glow, the universe bore witness to the birth of its very first luminous giants. These primordial objects, known to astronomers as population 3 stars, were, in their essence, unlike anything we observe in the cosmos today. They emerged from the pristine, unblemished gases left over from the Big Bang itself, a universe then composed almost exclusively of hydrogen and helium, and thus containing virtually no heavy elements. Their initial composition was a pure and simple blend of these two lightest elements, the only raw materials available in that nascent early era. Without the presence of heavier elements, which typically act as crucial coolants in the formation and evolution of modern stars, these population 3 stars grew to absolutely extraordinary sizes. Scientists believe they were hundreds of times more massive than our modest Sun, perhaps even reaching masses equivalent to several hundred suns, making them truly colossal. Such immense size meant they consumed their nuclear fuel at an astonishingly rapid rate, shining with a fiery brilliance that was truly spectacular, radiating light 1,000,000 times brighter than our own steady sun. Their lives, though undeniably glorious and impactful, were remarkably fleeting by cosmic standards, lasting only a few short million years before they gracefully reached their majestic end. These colossal, luminous pioneers were the very first to illuminate the universe, piercing the long era of cosmic darkness and initiating the crucial process of enriching the cosmos with the very first heavy elements. Their brief but intensely powerful existence laid the foundational chemistry for all subsequent generations of stars, galaxies, and eventually the complex structures that would emerge. Their light is gone now, but their fingerprints remain, subtle and quiet, in the chemical makeup of the ancient gas clouds and the underlying structure of the early cosmos, a silent legacy that continues to resonate through time, shaping everything that follows. All stars, without a single exception, including our familiar and life-giving Sun, begin their lives in a remarkably similar, gentle, and profoundly beautiful process. They are born from the slow, elegant collapse of vast, majestic clouds of gas and dust, ethereal structures known to astronomers as nebulae. These nebulae are, in essence, the universe's stellar nurseries, quiescent and often breathtakingly beautiful regions where the raw materials for new stars quietly gather and coalesce over eons. Within these immense, sprawling clouds, subtle gravitational instabilities begin to exert their gentle pull, drawing material inward. Over vast spans of cosmic time, tiny pockets of gas and dust slowly, almost imperceptibly, begin to coalesce, growing denser and warmer as more particles are drawn into their gravitational embrace. As more and more material accumulates, the gravitational pull at the center intensifies steadily, causing the entire cloud to shrink and, in many cases, to begin a slow, graceful rotation. This slow, inward collapse continues for many millions of years, transforming a diffuse cold cloud into a dense, intensely hot, and rapidly rotating core, often referred to as a protostar. Eventually, the pressure and temperature at the very heart of this collapsing mass becomes so extreme, so immense, that nuclear fusion ignites with a gentle, yet profound, burst of internal radiance. This moment marks the true birth of a star as it settles into a stable phase of its life, balancing the inward pull of gravity with the outward pressure from its fusion reactions. But not all stellar journeys lead to such a quiet, predictable end. For the most massive stars, their lives conclude in spectacles of extreme physics, leaving behind some of the universe's most astonishing remnants. Consider the neutron star, a silent, dense relic born from the heart of a massive star that has concluded its life in a grand, final burst of radiance. These incredibly compact objects represent a state of matter unlike anything we typically encounter. Imagine compressing the entire mass of our Sun, a star hundreds of thousands of times wider than Earth, into a sphere only about 20 kilometers across. The result is a neutron star, where gravity has crushed atoms so completely that protons and electrons merge, forming an almost pure sea of neutrons. This extreme compression leads to an unimaginable density. To give a sense of this, a mere single teaspoon of material taken from the core of a neutron star would possess a weight equivalent to billions of tons. To put that into perspective, it would outweigh Mount Everest many times over, all contained within a volume small enough to hold in your hand. This density defies our everyday experience, where even the heaviest materials on Earth feel light by comparison. It is a quiet testament to the immense forces at play during the final moments of a giant star, where matter itself is pushed to its absolute limits, becoming a silent, incredibly heavy core. The very structure of space and time around such an object is gently warped by its profound mass, creating a subtle gravitational well that is almost beyond comprehension. These tiny, city-sized powerhouses are not merely remnants. They are living laboratories of extreme physics, allowing us to glimpse the fundamental nature of matter under conditions that can never be replicated in any terrestrial setting. Their quiet existence speaks volumes about the universe's capacity for transforming the familiar into the truly extraordinary, leaving behind objects that are both immensely heavy and profoundly compact, anchors of gravity in the vast cosmic ocean. Further adding to the extraordinary nature of neutron stars is their incredible rotation. Many of these stellar remnants spin with astonishing speed, a consequence of the conservation of angular momentum as their progenitor stars collapsed. Among them are a particularly fascinating type known as millisecond pulsars. These compact objects can complete hundreds of rotations every single second, often spinning at rates exceeding 700 times per second. To visualize this, consider the speed of a typical kitchen blender blade, which operates at a fraction of this rotational velocity. Now, imagine an entire stellar core, a sphere with the mass of a sun, spinning at such dizzying rates. This rapid rotation creates an almost perfectly precise cosmic clock. As they spin, these pulsars emit beams of radiation from their magnetic poles. When these beams sweep across our line of sight, we detect them as rhythmic pulses of light or radio waves, much like the steady, precise beam from a cosmic lighthouse. These silent, rapid ticks are among the most stable timekeepers in the universe, a continuous, quiet rhythm emanating from the extreme physics of stellar death, providing astronomers with invaluable tools for studying the fabric of space-time itself. The regularity of their celestial beats allows scientists to observe subtle changes in the very fabric of the cosmos, making these fast-spinning stars silent, powerful instruments of discovery. Among the family of neutron stars, there exists an even more exotic and powerful member, the magnetar. These are neutron stars endowed with an unimaginably intense magnetic field, a force so profound it dwarfs anything we can comprehend on Earth. While our planet's magnetic field is strong enough to guide a compass needle, a magnetar's magnetic field can be trillions of times stronger. This colossal magnetic force is so potent that it could, in theory, erase all data from electronic devices thousands of kilometers away, or even distort the very atomic structures of matter in its immediate vicinity. It is a silent, invisible force, yet one of the most extreme phenomena in the cosmos. Scientists believe these incredible magnetic fields are formed during the dramatic collapse of a massive star, when convection and turbulence within the star's rapidly rotating core amplify the magnetic field to these astonishing levels, twisting and knotting the magnetic field lines until they reach an almost inconceivable intensity. The birth of a magnetar can also be linked to some of the universe's most powerful stellar explosions, known as hypernovae. While a typical supernova is a brilliant and awe-inspiring event, a hypernova is an even grander, more energetic spectacle. When a particularly massive star collapses and its core forms a magnetar, the immense energy released by the star's magnetic field as it settles and twists can drive an explosion that far surpasses the luminosity of a standard supernova. These hypernovae, sometimes associated with long-duration gamma-ray bursts, unleash a torrent of high-energy light that can briefly outshine entire galaxies. They are brief, intense bursts of radiance, lasting only a few seconds, yet their light can travel across billions of light years to reach us, carrying the quiet memory of a star's final, incredibly powerful act, a testament to the colossal forces at play when matter and magnetism reach their ultimate extremes. The sheer outpouring of energy from a hypernova is a quiet reminder of the hidden power contained within the very fabric of space, released in a gentle, yet monumental, cosmic exhalation. These events reshape their galactic neighborhoods, scattering newly forged elements far and wide, gently influencing the birth of future stars and planetary systems with their quiet, radiant legacy. While many massive stars conclude their lives in a magnificent supernova, a brilliant burst of radiance that seeds the universe with new elements, there is a more subtle, yet equally profound pathway to stellar death. For the most exceptionally massive stars, those at the very upper limits of stellar mass, their end can be strangely quiet, devoid of the expected cosmic fireworks. When these colossal stars exhaust their nuclear fuel, their immense gravitational pull becomes overwhelming. Instead of the outer layers being ejected in a grand, luminous explosion, the entire star's core and even its outer layers can collapse inwards so rapidly and completely that gravity triumphs without a visible struggle. The star simply implodes, its matter falling directly into the nascent black hole at its center. This process is known as a direct collapse. In these instances, there is no brilliant flash, no spectacular farewell, just a sudden, silent disappearance from the cosmic stage. Astronomers have, on rare occasions, observed stars that were once clearly visible in the night sky suddenly vanish without a trace, as if their light had simply blinked out. These quiet disappearances serve as a gentle reminder that not all cosmic endings are heralded by dramatic displays of light and sound. Some simply transition into the profound silence and invisibility of a newly formed black hole, a testament to the universe's capacity for both brilliant display and serene, unobserved transformation. They become the quiet, unseen devourers of light and time, leaving behind only a gravitational echo of their former brilliance. Even black holes, those anchors of space-time, are not entirely immune to cosmic motion. While they are often imagined as fixed points of immense gravity, they too can embark on journeys across the galaxy, pushed by the subtle yet powerful ripples of space-time. When two black holes, locked in a graceful cosmic dance, finally merge into a single, more massive black hole, the event sends out powerful gravitational waves. These ripples in space-time, predicted by Albert Einstein and now directly observed, carry away energy from the merging system. However, if the two original black holes are not perfectly symmetrical, or if their spins are misaligned, the emission of these gravitational waves can be uneven. This asymmetry acts like a gentle, subtle recoil, imparting a kick to the newly formed, larger black hole. This gravitational kick, though imperceptible to our senses, can be incredibly powerful, capable of accelerating the merged black hole to speeds of thousands of kilometers per second. Such a rapid acceleration can propel the black hole entirely out of its host galaxy, sending it drifting silently through intergalactic space, a solitary wanderer, forever separated from its cosmic birthplace. Other times, the kick might be less severe, simply altering its orbit within the galaxy, causing it to trace a wide, wandering path among the stars. These kicked black holes are extremely challenging to detect, as they are inherently invisible unless they interact with surrounding gas or stars, creating subtle disturbances that astronomers can painstakingly observe. Nevertheless, scientists believe they exist, quiet travelers pushed by the memory of their own colossal collision, a gentle reminder that even the heaviest and most profound objects in the universe are subject to the subtle forces and elegant dynamics of cosmic motion, never truly still, but always in a state of quiet, ceaseless drift, leaving a silent path through the cosmic tapestry. As we contemplate the profound movements of black holes, it is equally humbling to consider the sheer diversity in the sizes and temperatures of stars themselves. a spectrum that stretches from the truly immense to the barely perceptible, each a unique expression of cosmic physics. Among the most astonishing examples of stellar grandeur is the largest known star, a luminous supergiant designated Scuti. Its scale is almost impossible to grasp within our everyday frame of reference. If this colossal star were to be gently placed at the very center of our own solar system, its expansive outer layers would comfortably extend far beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars whole. Indeed, its vast diffuse atmosphere would reach out to encompass even the mighty gas giant, Jupiter itself, leaving our familiar planetary orbits deep within its fiery embrace. To travel around its equator at the speed of light, it would take several hours, a testament to its truly unimaginable circumference. Scuti is not merely large, it is an object of truly staggering proportions, a testament to the universe's capacity for producing structures on a scale that humbles the human imagination. Its immense size means it sheds vast amounts of material into space, contributing to the rich tapestry of interstellar gas and dust, a silent, continuous exhalation that enriches its cosmic surroundings. This star, glowing quietly in its distant corner of the galaxy, reminds us that our sun, while vital to our existence, is but a modest ember in a cosmos filled with truly gargantuan celestial fires, each a silent monument to the universe's grand scale and diversity. On the opposite end of the stellar size spectrum, we find stars that are barely large enough to qualify as stars at all. The smallest stars known to exist are truly diminutive by cosmic standards, possessing only about 8% of the mass of our Sun. This particular mass threshold is critically important, as it represents the minimum amount of gravitational compression required for a celestial body to ignite and sustain stable nuclear fusion in its core. Below this mass, the core of a protostar simply cannot generate enough pressure and temperature to initiate the fusion of hydrogen into helium. These tiny, low-mass stars are often called red dwarfs, and they burn their nuclear fuel at an incredibly slow and efficient rate. This gentle, measured consumption of hydrogen means they can live for truly immense periods of time, far longer than the current age of the universe itself, quietly glowing with a dim, reddish light for trillions of years. They are the marathon runners of the cosmos, enduring for eons, while more massive stars burn brightly and then fade away. Their quiet, persistent glow is a testament to the universe's efficiency, ensuring that even the most modest accumulations of matter can contribute to the cosmic light show, albeit in a subdued and long-lasting manner. These miniature stellar embers are the most numerous type of star in our galaxy, silent, persistent sentinels scattered throughout the cosmic night, each one a tiny, enduring furnace. Even more remarkably, some stellar remnants can be smaller than planets, presenting a fascinating paradox of cosmic scale. White dwarfs, the final gentle stage in the life cycle of stars like our Sun, offer a prime example of this extreme compression. After a star like our Sun expands into a red giant and then softly sheds its outer layers into space, what remains is its incredibly dense core. This core, now a white dwarf, is typically about the size of Earth, a mere fraction of its former self. Yet, despite its planetary dimensions, a white dwarf retains a substantial portion of its original stellar mass, often equivalent to that of our entire Sun. This means that matter within a white dwarf is incredibly compact, a testament to the immense gravitational forces at play. A single cubic centimeter of white dwarf material could weigh several tons, an astonishing density for an object the size of a world. These quiet, glowing embers no longer undergo nuclear fusion. Instead, they slowly radiate away their leftover heat over billions, even trillions of years, gradually dimming until they become invisible black dwarfs. They are silent, luminous fossils, quiet reminders of a star that once burned brightly, now slowly cooling in the cosmic dark, a planet-sized gem of compressed stellar history. The range of stellar temperatures is equally astonishing. stretching from the scorching infernos of massive blue stars to the barely glowing embers of the coolest celestial bodies. In a truly fascinating discovery, astronomers have identified objects that blur the lines between stars and planets, some of which are so cool that they are barely warmer than Earth's room temperature. These ultra-cool brown dwarfs, often referred to as failed stars, because they lack the sufficient mass to ignite sustained nuclear fusion, emit very little visible light. Their surface temperatures can drop to a mere few hundred degrees Celsius, which, while still hot by terrestrial standards, is incredibly cool for a celestial object. In fact, some of these enigmatic objects are so cool that they are only slightly warmer than a comfortable room on Earth, making them almost too faint to glow in the visible spectrum. We typically detect them through their faint infrared radiation, a subtle warmth that betrays their presence. These quietly glowing celestial bodies challenge our conventional definitions of what constitutes a star, revealing a spectrum of cosmic objects that exist in a transitional state between planet and star. They are silent, dim presences in the galaxy, almost invisible, yet they contribute to the quiet thermal background of the cosmos, a testament to the sheer diversity of celestial forms that can emerge from the universe's vast material. At the other extreme, the universe hosts stars that burn with an almost unimaginable intensity, radiating tremendous amounts of energy. The hottest stars are typically characterized by their striking blue or blue-white coloration. These are often massive young stars, consuming their nuclear fuel at an incredibly fast rate. Their surface temperatures can soar to tens of thousands of degrees Celsius, sometimes even exceeding 50,000 degrees Celsius. This extreme heat causes them to emit light predominantly in the blue and ultraviolet parts of the electromagnetic spectrum, giving them their characteristic hue. Their brilliant, intense glow illuminates vast regions of space, ionizing nearby gas and carving out luminous nebulae. Acting as cosmic beacons in stellar nurseries, these stars live fast and die young, burning through their fuel in a few million years. But during their brief, spectacular lives, they profoundly shape their galactic environments, seeding new generations of stars and planets with their radiant energy. Their silent, intense heat is a driving force in cosmic evolution, a powerful yet gentle sculptor of the interstellar medium. Conversely, the coolest stars in the universe present a much more subdued and tranquil appearance. These stars, often red dwarfs or red giants in their later stages of life, are defined by their distinct red coloration. Their surface temperatures can be remarkably low for a star, sometimes falling to around 2,000 degrees Celsius, while still incredibly hot compared to anything on Earth. This is significantly cooler than our Sun's surface temperature of about 5,500 degrees Celsius. This lower temperature means they emit most of their light in the red and infrared parts of the spectrum, giving them their characteristic deep red glow. Red dwarfs, in particular, are incredibly long-lived, burning their fuel so slowly that they can quietly persist for trillions of years. They are the quiet, enduring embers of the cosmos, providing a steady, gentle warmth to any potential orbiting worlds for eons. Their soft, reddish light is a testament to a slower, more deliberate form of stellar existence, a serene contrast to the fiery intensity of their blue counterparts. Perhaps one of the most immediate and visually striking indicators of a star's fundamental properties is its color. A star's color serves as a silent, immediate indicator of its surface temperature, offering a direct glimpse into its internal dynamics. Blue stars are the hottest, radiating at incredibly high temperatures. Their intense heat causes them to emit light across the electromagnetic spectrum, with a peak in the blue and ultraviolet wavelengths, giving them their brilliant azure or blue-white appearance. Conversely, the coolest stars are red, their lower surface temperatures causing them to emit light primarily, resulting in a deep, warm red hue. Stars like our Sun, which appear yellow-white, fall in between these two extremes, possessing moderate surface temperatures. This gentle color spectrum from brilliant blue to soft red, is not merely an aesthetic feature of the night sky. It is a fundamental property of stellar physics, reflecting the intricate balance of temperature, mass, and energy within each celestial body. By simply observing a star's color, astronomers can quietly infer a great deal about its nature, its age, and its place in the cosmic tapestry, a silent language spoken across vast distances, allowing us to understand the universe through the gentle hues of its luminous inhabitants. Our own sun, a familiar and comforting presence in our sky, also has a long and predictable journey ahead, a stellar life cycle that will unfold over billions of years. In the distant future, approximately 5 billion years from now, our sun will gently begin its transformation, swelling gracefully into a red giant. This serene expansion marks a significant shift in its stellar evolution. Having exhausted the primary hydrogen fuel in its core, the sun will begin to fuse hydrogen in a shell surrounding its now inert helium core. This change in its internal structure will cause its outer layers to expand dramatically and cool, giving it a distinct reddish hue and an immense size. As it gently expands, its outer atmosphere will gradually encompass the orbits of the innermost planets. Mercury and Venus, closest to the Sun, will be slowly absorbed into its vast, expanding embrace. There is also a possibility that Earth, our homeworld, will find itself enveloped within this grand, evolving star, becoming a part of its outer atmosphere. This is not a violent catastrophe, but rather a slow, majestic transformation, a natural and elegant progression in the life of a star like ours. The Sun will grow to hundreds of times its current diameter, becoming a truly colossal, albeit cooler, star. This future, though distant, is a testament to the quiet, ceaseless change that governs all celestial bodies, a gentle redefinition of our solar system's architecture over an unimaginable timescale. The familiar yellow-white sphere we see today will become a red giant, a beautiful, expanded form, a silent and inevitable chapter in its long cosmic story. This expansion will be a gradual process, taking millions of years, allowing its outer layers to softly reach outward, drawing in the inner worlds with a gentle, inexorable gravitational embrace. The energy that radiates so freely from the Sun's surface, warming our planet and sustaining life, embarks on an incredibly long and intricate journey from its birthplace deep within the Sun's core. Once generated through nuclear fusion, a single photon of light does not simply travel straight to the surface. Instead, it engages in what scientists describe as a random walk, a convoluted path that can take hundreds of thousands of years to complete. The Sun's interior is an incredibly dense environment, a hot, opaque plasma where photons are constantly absorbed and then re-emitted by countless atoms. Each time a photon is absorbed, it is then re-emitted in a completely random direction, causing it to bounce around endlessly within the Sun's radiative zone. This process is repeated countless times, millions upon millions of interactions, before the photon finally manages to escape into the convective zone and then, at last, emerges from the Sun's visible surface, the photosphere. This immense journey through the Sun's interior contrasts sharply with the relatively swift 8 minutes it takes for light to travel from the Sun's surface to Earth. It highlights the profound density and complexity of our star's internal structure, a silent, internal labyrinth where light particles spend eons navigating before they can finally stream out into the vastness of space. This slow, persistent diffusion of energy ensures a steady and stable output, a continuous flow of warmth that has nourished our world for billions of years, a testament to the Sun's quiet, enduring power. The journey of each photon is a silent epic, a long, slow dance through the Sun's fiery depths before it finally bursts forth to touch our world. At the very heart of the Sun, where the magic of stellar creation truly unfolds, lies a region of unimaginable heat and pressure. The Sun's core temperature is an astounding 15 million degrees Celsius. These extreme conditions are precisely what are required to overcome the natural electrical repulsion between atomic nuclei, allowing them to fuse together in the process of nuclear fusion. It is here, in this incandescent furnace, that 4 hydrogen nuclei are gently combined to form a single helium nucleus, releasing a tremendous amount of energy in the process. This energy, in the form of gamma rays and neutrinos, is the ultimate source of all the light and heat that the sun emits. The core is a dynamic and incredibly active region, a silent powerhouse where the fundamental forces of nature are engaged in a constant, delicate balance. Without this extreme temperature and pressure, the sun would simply be a large ball of gas, unable to generate its own light and warmth. The quiet intensity of the core is the engine that drives the entire star, a continuous, controlled reaction that has sustained our solar system for billions of years. It is a testament to the universe's ability to create pockets of extreme energy and transformation, essential for the ongoing cosmic cycle of element creation and stellar life. The 15 million degrees Celsius at its center represents the very crucible of creation, a silent forge where the universe builds its foundational elements. Our sun is currently about 4.6 billion years old, a comfortably middle-aged star. Having traversed roughly half of its projected lifespan on what astronomers call the main sequence. The main sequence phase is the longest and most stable period in a star's life, a time when it is actively fusing hydrogen into helium in its core. For our sun, this stable hydrogen-burning phase is expected to last for a total of approximately 10 billion years. This means that our sun has already spent a significant portion of its life providing a steady, reliable source of light and warmth to Earth, allowing for the emergence and evolution of life. As a main sequence star, the sun maintains a delicate balance between the inward pull of its own gravity, which constantly tries to compress it, and the outward pressure generated by the intense heat from its nuclear fusion reactions. This equilibrium ensures its consistent size and luminosity, providing the stable conditions necessary for planets like Earth to thrive. Knowing the sun's age and its position on the main sequence gives us a quiet sense of its enduring reliability, a celestial clock that has ticked with unwavering precision for billions of years and will continue to do so for billions more. It is a comforting thought, a quiet assurance of cosmic stability in an ever-changing universe, a steady beacon in the night sky. After its dramatic, yet gentle, red giant phase, the sun will undertake another beautiful transformation, evolving into what astronomers call a planetary nebula. This stage is a relatively brief but visually stunning chapter in a star's life. As the red giant's outer layers expand and become increasingly tenuous, they are gradually, softly shed into the vastness of space, drifting away from the star's core. This process creates an expanding shell of glowing gas around the now exposed, extremely hot and compact stellar core. The intense ultraviolet radiation emanating from this remnant core ionizes the expelled gas, causing it to glow with a myriad of vibrant colors, forming intricate and often breathtaking shapes in the cosmic canvas. These celestial formations are known as planetary nebulae, a name that is somewhat misleading as they have no direct connection to planets themselves. The term arose from early telescopic observations that sometimes made them appear round and planet-like. The central core left behind will be a white dwarf, the dense hot ember of the sun, quietly cooling over eons. The planetary nebula itself will expand and dissipate over tens of thousands of years, its beautiful ethereal glow gradually fading as its gases spread out and cool. This gentle dispersal of material serves a crucial cosmic purpose. It enriches the interstellar medium with newly created elements, providing the raw ingredients for future generations of stars and planetary systems. It is a quiet, artistic finale to a star's life, a beautiful, colorful exhalation that contributes to the ongoing cycle of cosmic creation and renewal, scattering its stardust back into the universe from which it came. The sun's gravitational influence extends far beyond the familiar orbits of our 8 planets. reaching into the deepest, coldest, and most distant regions of our solar system. Its powerful, yet gentle gravitational pull defines the vast, spherical expanse known as the Oort cloud. This immense, theoretical cloud of icy planetesimals is believed to encircle our entire solar system, stretching outwards to distances that are thousands of times farther than the orbit of Pluto. Imagine a vast, ethereal shell of billions or even trillions of icy bodies, remnants from the early formation of our solar system, quietly orbiting the Sun at an almost unimaginable remove. The Oort cloud is thought to be the reservoir for long-period comets, those celestial wanderers that occasionally make a dramatic, luminous visit to the inner solar system before returning to their distant, dark abode. These comets are gently dislodged from the Oort cloud by the subtle gravitational tugs of passing stars or galactic tides, beginning their long, slow journey inward. The existence of the Oort cloud is a quiet testament to the immense reach of the Sun's gravity, a force that silently organizes and holds together a vast, unseen realm of icy bodies at the very fringes of our stellar neighborhood. It reminds us that our solar system is far larger and more complex than the familiar planetary orbits suggest. A quiet, extended family of objects, all bound by the subtle, enduring embrace of our star's gravitational field. This vast, dark sphere is a silent, frozen archive of our solar system's birth, held gently in the Sun's distant sway. Finally, our Sun itself holds a specific place in the grand classification of stars. It is formally categorized as a G-type main sequence star, a designation that places it firmly within the most common and stable category of stars in the universe. While it is often colloquially referred to as a yellow dwarf, this term can be slightly misleading. From the pristine vacuum of space, the Sun actually appears white. Its yellowish tint when viewed from Earth is a gentle optical illusion caused by the scattering of blue light by our planet's atmosphere, allowing more of the yellow and red wavelengths to reach our eyes. As a main sequence star, the Sun is in the prime of its life, steadily and reliably converting hydrogen into helium in its core through nuclear fusion. This stable process ensures its consistent output of energy, which has been crucial for the development of life on Earth. G-type stars are known for their moderate temperatures, sizes, and luminosities, making them excellent candidates for hosting planetary systems capable of supporting life. Our Sun is a quiet, dependable star, neither exceptionally large nor small, neither incredibly hot nor cold, but perfectly suited to its role as the stable heart of our solar system. Its classification speaks to its balanced and enduring nature, a steady, white-hot beacon in the cosmic night that has quietly sustained quiet order and gentle rhythm of stellar existence. The serene, balanced existence of our Sun, while a testament to stellar stability, represents only one facet of the intricate and often surprisingly social lives of stars. Indeed, a significant number of stars in the cosmos do not journey through space alone. Instead, many are born in elegant partnerships, or even in graceful trios, locked in complex and enduring gravitational dances. These celestial pairings are known as binary or multiple star systems, and they are far more common than solitary stars like our Sun. Imagine 2, or sometimes 3, luminous spheres tracing intricate, harmonious orbits around a common center of mass, their gravitational embrace binding them together for billions of years. These stellar companions can be quite close, their atmospheres almost touching, or they can be separated by vast distances, their orbits unfolding over millennia. Each star in such a system exerts a gentle, continuous gravitational pull on its partner, creating a beautiful, ceaseless ballet in the emptiness of space. This quiet, orbital synchronicity is a testament to the fundamental force of gravity, weaving together individual stars into larger, interconnected celestial families, each contributing to the subtle rhythms of the galaxy. Their shared journey through the cosmos is a long, patient dance, a testament to the universe's capacity for intricate, enduring relationships, a silent symphony of orbital precision. In some of these close-knit binary systems, the gravitational intimacy between the stars can lead to remarkable and gentle exchanges of material, a cosmic interaction sometimes referred to as stellar cannibalism, though it is a far more elegant and less dramatic process than the name suggests. As one of the stars in the pair evolves, perhaps expanding into a red giant, its outer layers can extend outwards, coming under the gentle gravitational influence of its companion. When this occurs, the companion star can begin to softly siphon off material from its larger partner. This flow of gas typically forms a beautiful, glowing accretion disk around the receiving star, a swirling vortex of matter being gently transferred. This steady, quiet transfer of mass can profoundly alter the evolutionary paths of both stars. The donor star may gradually lose a significant portion of its mass, revealing deeper, hotter layers, while the recipient star becomes more massive and luminous, potentially changing its classification and lifespan. Such delicate exchanges can lead to a wide array of fascinating stellar phenomena, from bright bursts of light to the eventual formation of exotic objects like white dwarfs or neutron stars. These interactions are not violent collisions, but rather slow, graceful dances of matter and gravity, a continuous, subtle reshaping of stellar destinies played out over millions of years, a quiet blending of their individual lives into a shared cosmic narrative. It is a profound example of how stars, in their quiet proximity, can mutually influence and redefine one another's existence. The presence of multiple stars in a system doesn't necessarily preclude the formation and stable existence of planets. Indeed, astronomers have discovered worlds that serenely orbit binary stars, creating the captivating spectacle of a sky adorned with two suns, much like the iconic fictional world of Tatooine. These are known as circumbinary planets, and their existence confirms the universe's boundless capacity for planetary diversity. Imagine a world where dawn brings not one, but two sunrises, painting the sky with a double palette of light and shadow. The orbital mechanics for such planets are understandably more intricate than those in our single-star solar system, yet they are remarkably stable, allowing these worlds to maintain their graceful paths around their dual parent stars. The gravitational forces from two stars create a complex but predictable environment, where a planet can find a stable orbit if it is sufficiently far from the stellar pair. These discoveries have expanded our understanding of where planets can form and thrive, gently pushing the boundaries of what we once considered possible. Worlds with two suns offer a quiet, beautiful vision of cosmic variation, reminding us that the familiar single-star system of our Earth is just one of many elegant arrangements that can arise in the vast cosmic tapestry, each offering a unique perspective on the interplay of light and gravity. The gentle, shifting glow from two stars would cast long, dancing shadows, creating a unique and tranquil rhythm of day and night. While many stars remain gravitationally bound within their birth clusters or binary systems, not all are destined for such communal journeys. Some stars embark on solitary paths, becoming quiet wanderers across the vastness of space, gently ejected from their stellar birthplaces. This often occurs in dense star clusters, where close encounters between multiple stars can lead to powerful gravitational interactions. In a cosmic dance of subtle pushes and pulls, a star can gain enough velocity from these interactions, much like a gravitational slingshot, to gently break free from the collective gravitational embrace of its cluster. Once ejected, these stars become unbound, silently drifting away from their stellar families, traversing the interstellar medium alone. They are like cosmic nomads, leaving behind the bustling stellar nurseries where they were born to embark on an independent journey through the quiet dark. These solitary wanderers, though less numerous than their clustered counterparts, are a testament to the dynamic and ever-changing nature of stellar environments. where even the most tightly bound groups can experience the gentle dispersal of their members. Their silent, unhurried passage through space is a poignant reminder of the universe's capacity for both connection and quiet solitude, each star tracing its own unique, unbound path through the cosmic expanse. Extending this idea further, there are also truly rogue stars that drift through galaxies, completely unattached to any specific star system or cluster. These are the ultimate cosmic loners, traversing the vast intergalactic void without the gravitational anchor of a parent star or a stellar family. Unlike stars gently ejected from clusters, these rogue stars might have formed in isolation, far from dense nebulae, or perhaps they were stripped from smaller, less stable systems that were disrupted by larger galactic forces. They move silently through the galaxy, their paths often taking them far from the luminous spiral arms, into the quieter, darker regions of the galactic halo, or even into the spaces between galaxies. Detecting these wandering stars is a subtle challenge for astronomers, as they are often dim and isolated, their presence revealed only by their faint light or their gentle gravitational influence on other objects. Their existence paints a picture of a dynamic cosmos, where not every star is part of a grand design or a discernible pattern. Instead, some simply drift, following their own quiet trajectories, silent, luminous points of light moving through an otherwise empty canvas. Each one is a testament to the universe's vastness, a quiet reminder that even in the grand tapestry of galaxies, there are individual threads that unravel and journey alone, tracing a path of quiet independence through the cosmic ocean. On an even grander scale of cosmic interaction, our own Milky Way galaxy is engaged in a profound and elegant celestial dance with its closest large galactic neighbor, the Andromeda Galaxy. These two immense spiral galaxies are currently on a slow, inexorable collision course, a gravitational embrace that will unfold over billions of years. At present, Andromeda is approximately 2.5 million light-years away from us, a significant but steadily closing gap. In about 4 billion years, the two galaxies will begin their graceful merge. However, it's a fascinating detail that the outer halos of both galaxies, which are vast, diffuse clouds of hot gas and dark matter extending far beyond their visible stellar disks, are already subtly overlapping. In this sense, the two colossal systems have already begun their gentle interaction, quietly touching across immense cosmic distances. The eventual merger will not be a catastrophic crash of stars, as the vast distances between individual stars mean that direct star-on-star collisions will be incredibly rare. Instead, it will be a slow, elegant blending, a graceful rearrangement of billions of stars, gas, and dust. Over eons, the two distinct spiral shapes will gradually coalesce into one much larger, more elliptical galaxy. Astronomers have affectionately dubbed this future galactic entity Milkomeda, a quiet testament to the eventual union of these two majestic systems. This grand cosmic meeting is already in motion, a silent dance playing out over unimaginable timescales, a beautiful and inevitable transformation that will reshape our galactic neighborhood with quiet grace. This gentle merging of galaxies is a testament to the universe's continuous evolution, a silent, ongoing process of growth and transformation. It reminds us that even the largest structures in the cosmos are not static, but are constantly engaged in subtle interactions that reshape their forms and destinies. The gravitational pull between galaxies orchestrates these grand dances, leading to mergers that gradually build larger and more complex systems. The outer halos, those invisible envelopes of dark matter and sparse gas, are the first to encounter each other, initiating the long process of integration. This quiet initial overlap is a precursor to a more complete, yet still gentle blending of stellar populations and interstellar material. The stars themselves, rather than colliding, will mostly pass by one another, their individual orbits gently perturbed and redirected by the immense gravitational fields of the two merging galaxies. Over hundreds of millions of years, the familiar spiral arms will slowly unravel and reform, eventually settling into a new, more elliptical configuration. This transformation is a cosmic ballet of immense proportions, a slow, majestic unfolding that speaks to the universe's capacity for grand-scale, yet unhurried, change. The quiet, inexorable pull of gravity guides these colossal systems, transforming two distinct entities into a unified, larger whole, a silent testament to the enduring power of cosmic attraction. It is a future written in the gentle curves of space-time, a beautiful, inevitable resculpting of our galactic home. The quiet intertwining of these vast systems will be a long, serene process, culminating in a new, unified cosmic entity that will shine with a combined brilliance. This grand galactic evolution is a beautiful testament to a fundamental truth of stellar existence. A star's eventual fate is determined primarily by its initial mass. From the moment of its birth, the amount of material gathered by a forming star dictates its internal pressure, its core temperature, the types of nuclear fusion it can sustain, and ultimately, the elegant manner in which its life will conclude. Whether it gently fades over eons, swells into a luminous giant, or collapses into an incredibly dense remnant or a profound black hole, every star's destiny is quietly inscribed within its mass at the very beginning of its luminous journey. This foundational principle shapes the entire narrative of stellar evolution, creating the diverse array of celestial objects we observe across the cosmos, each following its own predestined path, a quiet unfolding of cosmic physics. Among the most enduring and tranquil of all stellar inhabitants are the red dwarf stars. These diminutive celestial bodies represent the lower limit of what can truly be considered a star. Due to their modest mass, red dwarfs engage in nuclear fusion at an incredibly slow and remarkably efficient rate, conserving their hydrogen fuel with an almost unparalleled frugality. This measured consumption allows them to live for truly immense spans. Scientists estimate that red dwarfs can quietly burn their fuel for trillions of years, a timescale that stretches beyond our comprehension. While they emit only a dim, reddish light, their sheer longevity means they embers scattered throughout the cosmic night. They are the patient sentinels of the universe, offering a quiet, stable source of warmth and light for potential worlds for unimaginably long periods, a testament to the universe's capacity for gentle, enduring existence. Their quiet glow will persist long after more massive stars have faded, a steady, unwavering presence in the deepening cosmic twilight. In contrast, stars of medium mass, like our own Sun, follow a different, yet equally graceful, evolutionary path after their main sequence lives. The term red giant refers to a star that has exhausted its primary hydrogen fuel in its core and, in response, has expanded dramatically in size. This transition is a gentle, internal restructuring. With core hydrogen fusion ceasing, the core begins to contract under its own gravity, causing it to heat up. This increased core temperature then ignites hydrogen fusion in a shell surrounding the now inert helium core. The energy released from this shell fusion pushes the star's outer layers outward, causing them to swell to immense proportions and cool down, giving the star its characteristic reddish hue. A red giant can become hundreds of times larger than its original size, a luminous, expanded sphere gently shedding its outer layers into space. This phase is a temporary, yet beautiful transformation, marking a star's serene transition from its stable, hydrogen-burning life to its final, more compact forms. It is a slow, majestic exhalation of stellar material, quiet reshaping of its cosmic neighborhood. Following the red giant phase for low to medium mass stars, the outer layers continue to drift away, forming a beautiful, ethereal planetary nebula. What remains at the heart of this dispersing cloud is a white dwarf, a dense, hot remnant about the size of Earth, comparable to that of our Sun, compressed into an incredibly compact volume. The matter within a white dwarf is so dense that a single cubic centimeter would weigh several tons, a profound testament to the power of gravity. These celestial embers no longer generate energy through a process that takes billions, even trillions of years. Over these immense timescales, a white dwarf will gradually dim, its faint glow slowly fading until it becomes a hypothetical black dwarf, a cold, dark, and invisible remnant. Every white dwarf observed today is still quietly glowing, a luminous fossil gently cooling in the cosmic dark, a quiet, enduring monument to stellar transformation. For stars far more massive than our Sun, their end is a more dramatic, yet still profoundly natural process. When these colossal stars exhaust their fuel, their cores collapse inward with immense gravitational force. This collapse triggers a magnificent, final burst of radiance known as a supernova, scattering most of the star's outer layers into space. What remains at the heart of this cosmic exhalation is a neutron star, the superdense core left behind. These objects are incredibly compact, typically only about 20 kilometers in diameter, yet they contain the mass of 1.5 to 3 suns. The matter within a neutron star is so compressed that electrons and protons have merged into neutrons, creating a state of matter so dense that a single teaspoon of it would weigh billions of tons. Neutron stars are the densest objects in the universe, short of black holes, and represent a quiet, extreme state of matter, a silent, heavy memory of a star that once blazed with incredible power. Their existence is a testament to gravity's profound ability to reshape matter into its most compact and exotic forms, a quiet, enduring presence in the cosmic void. For the most massive stars, those at the absolute upper limits of stellar mass, the gravitational forces at play are so immense that even a neutron star cannot withstand the inward pull. When these stars conclude their lives, their cores collapse completely, leading to the formation of a black hole. A black hole is not an object in the traditional sense, but rather a region of space-time where gravity is so overwhelmingly strong that nothing, not even light, can escape its embrace once it crosses a boundary called the event horizon. These profound gravitational wells are often formed from the direct collapse of massive stars, where the star's core implodes without the outward burst of a supernova, simply vanishing from view. The gravity within a black hole warps space-time itself, creating a funnel-like distortion where all paths lead inward to a singularity, a point of infinite density. They are silent, invisible devourers of light and time, yet their presence is profoundly felt through their gravitational influence on surrounding matter and the gentle bending of light. Black holes are the ultimate expression of gravity's power, a quiet, profound mystery at the heart of the cosmos, representing the serene, ultimate end for the most colossal stars, a final, unobserved transformation into pure gravitational presence. Beyond the realm of true stars, there exists a fascinating category of celestial objects known as brown dwarfs, often affectionately referred to as failed stars. These enigmatic bodies occupy a transitional space between giant planets and small stars. They are too massive to be considered planets, yet they are too small to sustain stable nuclear fusion of hydrogen into helium in their cores, which is the defining characteristic of a true star. Brown dwarfs do generate some heat and light through gravitational contraction and the temporary fusion of deuterium, a heavier isotope of hydrogen. However, this process is not sustained for long. As they age, they slowly cool and dim, radiating mostly in the infrared part of the spectrum, making them difficult to detect. Their dim, quiet glow means they are often invisible to optical telescopes, appearing as faint smudges in the cosmic dark. Brown dwarfs are a testament to the subtle variations in cosmic formation, representing masses that fell just short of achieving full stellar ignition. They are quiet, enduring presences, slowly cooling embers in the galactic void, reminding us that the universe is filled with a spectrum of celestial bodies, each with its own gentle, unique story of formation and evolution, a quiet continuum between the largest planets and the smallest stars. Their presence adds a layer of subtle complexity to the stellar census, enriching our understanding of the diverse outcomes of cosmic birth. Beyond these grand galactic ballets, individual stars also exhibit a fascinating array of unique phenomena and quirks, revealing their dynamic and often subtle internal lives. One of the most intriguing discoveries is that stars can, in a manner of speaking, sing through their internal vibrations. This isn't sound as we perceive it in the vacuum of space, which carries no air to transmit sound waves. Instead, these are deep, slow pressure waves that ripple and resonate through the star's superheated plasma, much like seismic waves traveling through the Earth's interior. These internal oscillations cause the star's surface to gently pulse and subtly change shape. Scientists have developed a specialized field of study called asteroseismology, literally the seismology of stars, to detect and interpret these faint stellar vibrations. By meticulously observing tiny, almost imperceptible changes in a star's brightness or the gentle movements of its surface, astronomers can listen to these silent cosmic melodies. Each star possesses its own unique set of internal frequencies, a kind of gravitational fingerprint determined by its specific size, its intricate internal structure, and its current age. By carefully analyzing these stellar songs, scientists can peer deep inside stars, much like using ultrasound to learn what is happening beneath their luminous exteriors. This provides invaluable insights into their density profiles, their internal rotation rates, and even the complex flow patterns of their hot gases. It is a quiet, profound form of cosmic echolocation, a way to gently hear the music of stars across immense light years, even if the grand symphony remains silent to human ears, a testament to the subtle, rhythmic life within each stellar body. Furthermore, not all stars maintain a constant, unwavering glow. Some celestial bodies appear to flicker or subtly change their brightness in rhythmic patterns, earning them the classification of variable stars. These stars pulse with a slow, captivating stellar rhythm, their luminosity gently waxing and waning over periods that can range from a few hours to many months or even years. This intrinsic variability is not due to external factors like eclipsing planets, but rather to dynamic processes occurring within the stars themselves. In many cases, these pulsations are caused by changes in the star's outer layers, where gases gently expand and cool, then slowly contract and heat up again in a continuous, graceful cycle. This delicate interplay of internal pressures and temperatures creates a steady, predictable beat. These rhythmic variations are remarkably consistent in many types of variable stars, making them invaluable celestial clocks for astronomers. By carefully observing their pulsation patterns and measuring the period of their brightening and dimming cycles, scientists can use them as cosmic yardsticks to determine immense distances across the universe. A single flicker, repeated over and over with quiet precision, can unlock the secrets of a star's true brightness and its exact position in the vast cosmic tapestry, allowing us to map the universe with a gentle, rhythmic guide. These stars are living, breathing beacons, quietly broadcasting information across the void. Stars also exhibit bursts of intense activity on their surfaces, known as stellar flares, which are powerful bursts of radiation. While our own sun produces solar flares, these events on other stars can sometimes be many times larger and significantly more energetic than anything observed from our sun. These flares are thought to be caused by the sudden, elegant reconnection of complex magnetic field lines within the star's atmosphere, releasing vast amounts of stored energy in an instant. This release manifests as a sudden, intense brightening across various wavelengths, including X-rays, ultraviolet light, and visible light. While these flares are powerful, they are a natural part of a star's magnetic activity, a gentle release of accumulated energy. For stars with orbiting planets, particularly those in close proximity, such flares could have profound implications for atmospheric chemistry and habitability, a quiet yet potent influence on their planetary companions. These bursts are a reminder of the subtle, yet immense magnetic forces at play on stellar surfaces, a continuous dynamic interplay that occasionally manifests in these radiant, though non-dramatic, exhalations of energy, contributing to the quiet, ceaseless activity of the cosmos. In a related phenomenon, stars can also have spots on their surfaces, analogous to the sunspots we observe on our own sun, but often on a much grander scale. These stellar spots are regions of intense magnetic activity, where the star's internal convection is inhibited, causing the surface temperature to drop slightly and appear darker than the surrounding areas. While sunspots on our sun are relatively modest in size, lasting for days or weeks, the spots on other stars can be many times larger and significantly more powerful, sometimes covering a substantial fraction of the star's visible surface. These immense stellar spots can cause noticeable, yet gentle variations in the star's overall brightness as they rotate into and out of view. They are quiet indicators of the star's deep magnetic dynamics and rotational characteristics. The presence and movement of these spots allow astronomers to study a star's rotation rate and the complex patterns of its magnetic field, offering a silent window into the star's hidden internal workings. These cosmic blemishes are not imperfections, but rather beautiful, natural expressions of a star's magnetic life, subtly influencing its radiant output with their quiet, shifting presence. Our sun, in particular, exhibits a predictable and gentle rhythm in its activity, marked by an approximately 11-year activity cycle. This cycle is characterized by a gradual rise and fall in the number of sunspots visible on its surface, as well as a corresponding increase and decrease in the frequency and intensity of solar flares and other energetic events. During the peak of the cycle, known as solar maximum, the sun is adorned with numerous sunspots, and solar flares are more common and powerful. Conversely, during solar minimum, the sun's face appears relatively calm and unblemished, with fewer sunspots and less frequent flaring. This 11-year rhythm is intrinsically linked to the sun's magnetic field, which undergoes a graceful reversal of its polarity at the peak of each cycle. This predictable, yet profound, magnetic dance ensures a continuous quiet variation in the sun's output, subtly influencing space weather around Earth. The sun's activity cycle is a testament to its internal stability and its gentle, long-term predictability, a silent, rhythmic breathing that has persisted for billions of years, providing a steady, reliable rhythm to our solar system. It is a quiet, internal clock, marking the passage of stellar time with unwavering precision. Contrary to the idealized images often depicted, stars are not perfectly spherical celestial bodies. Their rapid rotation causes a slight, yet measurable bulge at their equator, giving them an oblate spheroid shape, much like a gently flattened sphere. This subtle distortion is a direct consequence of centrifugal force, the outward push generated by the star's spin. As a star rotates, the material at its equator experiences a greater outward force than the material at its poles, causing it to gently spread outwards. The faster a star spins, the more pronounced this equatorial bulge becomes, while for a relatively slow rotating star like our Sun, this flattening is barely perceptible. For very rapidly rotating stars, the effect can be quite dramatic, making them visibly wider at their middle than they are tall. This gentle reshaping of a star's form is a beautiful illustration of the interplay between gravity, which pulls matter inward, and rotational forces, which push it outward. It is a quiet, elegant testament to the dynamic nature of celestial mechanics, revealing that even the most massive and seemingly perfect objects in the universe are subtly molded by the forces that govern their existence, forever dancing between perfect form and the gentle distortions of motion. Finally, stars can also experience phenomena akin to starquakes, which are sudden, gentle shifts in their internal structure that cause subtle vibrations and observable changes in their brightness. These internal adjustments are not violent ruptures, but rather quiet releases of accumulated stress within the star's layers, perhaps due to changes in convection, magnetic fields, or the gradual settling of its dense core. When a starquake occurs, it sends ripples of pressure and motion through the star's interior, similar to how an earthquake sends seismic waves through Earth. These vibrations can cause the star's surface to subtly oscillate, leading to small, temporary variations in its luminosity that astronomers can detect with sensitive instruments. Studying these starquakes, often through the techniques of asteroseismology, provides invaluable insights into the star's internal composition, its density profiles, and the dynamics of its deep interior. They are like quiet murmurs from within, revealing the hidden life and subtle transformations occurring deep beneath a star's radiant surface. These gentle tremors are a reminder that stars, though seemingly stable, are dynamic systems, constantly making small, internal adjustments as they gracefully age, their quiet vibrations echoing across the vastness of space, a silent communication from the heart of a distant sun. This internal life of stars, however, is often perceived through a filter of immense cosmic distance and the subtle distortions of perception, revealing a complex interplay of light, time, and the very fabric of space. One of the most profound aspects of observing the cosmos is the understanding that the light from some stars we behold tonight left them billions of years ago, offering us an unparalleled glimpse into the cosmic past. When we gaze at a distant galaxy, or even a star far within our own Milky Way, we are not seeing it as it exists in this very moment. Instead, we are looking back in time, witnessing light that embarked on its journey across the vast expanse of the universe untold ages ago. Imagine the light from a faraway stellar nursery where new stars are gently igniting, beginning its long voyage across expanding space. That light may have traveled for 5 billion, 8 billion, or even 10 billion years before finally reaching our telescopes or our eyes. This means we are seeing those celestial objects as they were when the universe was significantly younger, perhaps before our own sun was born, or even before Earth had fully formed. Each photon that touches our retina or activates a sensor on a telescope carries with it a silent, ancient story, a frozen snapshot of a moment in cosmic history. This phenomenon transforms every deep sky image into a kind of time machine, allowing astronomers to quietly piece together the evolutionary narrative of the universe, observing galaxies in their infancy and stars in their earliest, most energetic phases. It is a humbling realization, a gentle reminder that the night sky is not a static canvas, but a living archive of time, where the past continually unfolds before our very eyes, a quiet echo from the universe's long and graceful journey. The sheer scale of these light travel times underscores the immense distances involved, making each distant pinpoint of light a profound connection to an ancient, vanished epoch, a silent whisper from the dawn of creation, softly arriving across unimaginable stretches of space. Paradoxically, the beautiful twinkling effect we often observe when looking at stars is not an inherent property of the stars themselves, but rather a gentle distortion caused by Earth's own atmosphere. Stars are, in fact, steady, unwavering beacons of light, emitting a continuous glow. The shimmering, dancing appearance we perceive is due to the constant movement and varying densities of air in our planet's atmosphere. Different layers of air with slightly different temperatures and pressures act like tiny, shifting lenses, gently bending and refocusing the starlight as it travels towards our eyes. As these atmospheric pockets move and churn, the path of the starlight is subtly altered, causing the star's apparent brightness and position to flicker rapidly. This effect is known as atmospheric turbulence. Planets, by contrast, appear much steadier in the night sky because they are significantly closer to Earth and thus present a larger apparent disk. Light from a planet arrives at our eyes as a bundle of many parallel rays, which are less susceptible to the individual distortions of atmospheric turbulence. The effects tend to average out, resulting in a more constant, gentle glow. So, while the twinkling of a star adds a touch of ethereal beauty to the night, it is a purely terrestrial phenomenon. A quiet dance between ancient starlight and our planet's ever-moving envelope of air, a beautiful illusion woven by the gentle breezes and thermal currents high above us, a testament to the subtle interaction between the cosmos and our immediate surroundings. The star itself, far beyond, remains a constant, serene source of light, unperturbed by the atmospheric ballet that transforms its distant glow into a shimmering jewel. Bringing this concept of light travel time closer to home, the light from our own sun takes approximately 8 minutes to reach Earth, traveling at the universe's ultimate speed limit, the speed of light. This means that when you look at the sun, you are seeing it as it was 8 minutes and 20 seconds ago, a tiny yet significant delay in cosmic communication. If, by some unimaginable event, the sun were to suddenly and silently vanish from existence, we would not know about it for another 8 minutes, as its final rays of light would continue their journey across the 93 million miles separating us, gently illuminating our world before darkness finally descended. This 8-minute journey is a fundamental constant in our solar system, a quiet reminder of the finite speed at which information can travel through space. It highlights the profound interconnectedness of our planet with its parent star, a continuous flow of energy that sustains all life, yet always with that subtle, inherent delay. This gentle lag in light's journey underscores the vast, quiet distances even within our own cosmic neighborhood, a constant, unhurried passage of radiant energy that shapes our days and nights, a testament to the steady, unyielding rhythm of the cosmos, where even the most immediate light takes its own measured time to arrive. To bridge these immense cosmic distances, astronomers use a specialized unit of measurement, the light year. It is crucial to remember that the term light year is a measure of distance, not of time, despite its evocative name. It represents the staggering distance that light, traveling at its constant speed of approximately 300,000 kilometers per second, can cover in a single Earth year. To put this into perspective, 1 light year is equivalent to about 9.5 trillion kilometers, or approximately 6 trillion miles. This immense unit helps us to quietly comprehend the truly vast scales of interstellar and intergalactic space. Without such a measure, the numbers required to describe the distances between stars and galaxies would become unwieldy and almost meaningless. For instance, the nearest star system to our Sun, Alpha Centauri, is about 4.37 light-years away, meaning the light we see from it today began its journey over 4 years ago. Galaxies, on the other hand, can be millions or even billions of light-years distant, each light-year marking another step across the silent, expanding canvas of the universe. The light year serves as a gentle cosmic ruler, allowing us to map the immense emptiness between celestial objects and to quietly appreciate the truly vast and sprawling nature of our universe, where even light, the fastest thing we know, takes eons to traverse the silent, boundless distances. Measuring these incredible distances requires ingenious methods. And for relatively nearby stars, astronomers employ a technique called stellar parallax. This concept is based on a simple geometric principle. As Earth gracefully orbits the Sun, our vantage point in space subtly changes over the course of 6 months. By observing a nearby star from 2 different positions in Earth's orbit, separated by approximately 300 million kilometers, astronomers can detect a tiny, apparent shift in the star's position against the backdrop of much more distant, seemingly fixed background stars. Imagine holding your finger out at arm's length and alternately closing one eye and then the other. Your finger appears to shift against the distant wall. Stellar parallax works on the same principle, but on a cosmic scale. The angle of this minute shift, known as the parallax angle, is inversely proportional to the star's distance. The smaller the angle, the farther away the star. This method allows for remarkably precise measurements of distances to stars within a few hundred light-years of Earth. It is a quiet triumph of geometry and observation, transforming the Earth's annual journey around the Sun into a cosmic baseline for measuring the depths of space, providing a fundamental rung on the ladder of cosmic distances and allowing us to gently map our immediate stellar neighborhood with quiet precision. Beyond the visible light that our eyes can perceive, stars are truly multifaceted emitters, radiating energy across the entire electromagnetic spectrum. Visible light, the familiar hues of a rainbow, constitutes only a tiny fraction of the total energy a star releases. Stars also gently emit X-rays. Ultraviolet light, infrared radiation, radio waves, and gamma rays. Each of these different wavelengths carries unique information about the star's properties and processes. X-rays, for example, often originate from extremely hot regions, such as a star's corona, the superheated outer atmosphere, or from the violent interactions in binary systems. Ultraviolet light comes from energetic processes in a star's upper atmosphere. Infrared radiation, by contrast, is often associated with cooler regions, such as dust clouds surrounding young stars or the faint glow of brown dwarfs. Radio waves can be emitted by complex magnetic fields or by the rapid rotation of neutron stars. To capture this full, rich spectrum of stellar emission, astronomers must utilize a variety of specialized telescopes, many of which are located in space, beyond Earth's absorbing atmosphere. By studying a star's light across all these wavelengths, scientists can piece together a much more complete and nuanced understanding of its internal workings, its surface activity, and its interactions with its environment. It is a silent, continuous broadcast of information, a gentle symphony of radiation that reveals the hidden life and profound complexity of stars, extending our perception far beyond the limits of human vision, allowing us to quietly listen to the universe's full range of silent frequencies. In a truly remarkable interplay of light and shadow, some stars appear to blink with a gentle rhythmic dimming when an exoplanet passes directly in front of them from our vantage point. This event is known as a transit, and it has become one of the most successful methods for detecting planets orbiting other stars. When an exoplanet crosses the face of its host star, it briefly blocks a tiny fraction of the star's light, causing a subtle, temporary dip in the star's observed brightness. This gentle dimming is usually very small, often less than 1% of the star's total light, requiring incredibly sensitive instruments to detect. However, if this dimming recurs at regular intervals, it provides compelling evidence for the presence of an orbiting planet. The duration of the transit, the depth of the dimming, and the frequency of these blinks can all provide valuable information about the exoplanet's size, its orbital period, and even its atmospheric composition. This quiet, repetitive signal has allowed astronomers to discover thousands of exoplanets, revealing a vast and diverse population of worlds beyond our solar system. Each gentle blink of a distant star is a silent confirmation of a hidden world, a subtle celestial announcement that another planet is tracing its quiet path around a faraway sun, a testament to the universe's endless capacity for planetary systems, each one a tiny, elegant interruption in the steady flow of starlight. The universe, in its boundless capacity for intricate arrangements, presents us with not only individual stellar dramas and planetary revelations, but also the grand, sweeping narratives of stellar populations and their collective structures. It is a quiet testament to the ever-evolving nature of galaxies that some stars are, in fact, older than the very galaxies they currently call home. This fascinating phenomenon arises from the slow, elegant process of galactic growth, where larger galaxies gradually coalesce and expand by gently merging with smaller, less massive systems. Imagine a grand cosmic dance unfolding over billions of years, where countless smaller stellar islands are softly drawn into the gravitational embrace of a larger spiral or elliptical system. During these graceful mergers, the stars that once belonged to the smaller absorbed galaxies continue their individual journeys, now integrated into the fabric of their new, larger host. These ancient traveler stars, having witnessed the birth and demise of their original galactic homes, carry with them the quiet memory of a different cosmic era. They are often found in the outer halos of galaxies or in streams of stars that bear the indelible, subtle mark of their past origins. Their chemical compositions might subtly differ from the stars born within the larger galaxy, offering astronomers a quiet, invaluable clue to their ancient heritage. These stellar elders float serenely through their adopted homes, silent survivors of earlier cosmic encounters, their light a soft echo from a time when the universe was structured differently, a testament to the continuous, gentle reshaping of galactic landscapes. Their presence reminds us that galaxies are not static, unchanging entities, but rather dynamic, living systems that grow and evolve through a long, patient process of accretion and integration, slowly weaving together the stellar tapestries of the cosmos. Each of these ancient stars is a quiet, luminous fossil, preserving a fragment of an earlier, vanished epoch, a gentle whisper of galactic ancestry carried across immense spans of space and time. They are the quiet witnesses to the universe's ceaseless, elegant transformation, their enduring light a beacon of cosmic history. Within the vast, quiet expanse surrounding galaxies, there exist some of the most venerable and awe-inspiring stellar structures known, globular clusters. These are ancient, densely packed groups of stars, often containing hundreds of thousands, or even millions, of individual suns, all gravitationally bound into a single, majestic, spherical ball. Unlike the stars in the main disk of a galaxy, which typically orbit in a flat plane, globular clusters trace long, sweeping paths through the galactic halo, a vast, diffuse sphere of gas and dark matter that envelops the visible galaxy. These clusters are among the oldest objects in the universe, with many of their stars being nearly as old as the cosmos itself, often 13 billion years or more. Their stars are typically metal poor, meaning they contain very few elements heavier than hydrogen and helium, a quiet indication of their ancient origins from the early universe. The immense gravitational pull within a globular cluster means that its stars are incredibly tightly packed, particularly towards the center, creating a shimmering, luminous core where stars are far closer to each other than in our own stellar neighborhood. Despite their density, these clusters are remarkably stable, enduring for billions of years as silent, majestic satellites, gracefully orbiting their host galaxies. Each globular cluster is a quiet, self-contained universe of ancient light, a shimmering ball of stellar history, providing astronomers with invaluable insights into the early formation and evolution of galaxies. They are like quiet, living museums of the cosmos, preserving a pristine sample of the universe's earlier stellar populations. Their collective glow, a soft, enduring beacon from the dawn of time, a testament to the beautiful, enduring power of gravity to bind countless stars into a harmonious, ancient whole, tracing their patient, silent orbits through the galactic night. In gentle contrast to the ancient, tightly bound globular clusters, we find the more youthful and loosely arranged groupings of stars known as open clusters. These stellar nurseries are typically found within the spiral arms of galaxies, the very regions where new stars are actively and quietly forming from collapsing clouds of gas and dust. Open clusters usually contain a few hundred to a few thousand stars, a more modest population compared to their globular counterparts. The stars within an open cluster are relatively young, often having formed at roughly the same time from the same initial nebula, making them stellar siblings that share a common origin. Unlike globular clusters, which are held together by immense gravity for billions of years, open clusters are more transient and less densely packed. Their gravitational bonds are weaker, and over time, they slowly disperse as their member stars gently drift apart due to gravitational interactions with other stars, gas clouds, and the broader tidal forces of the galaxy. This dispersal is a slow, elegant process, a gradual unbinding of stellar families as they embark on their individual journeys through the galactic disk. Open clusters appear as beautiful, glittering collections of young, bright stars, often still nestled within the wisps of the gas and dust from which they were born. They serve as quiet indicators of ongoing star formation, luminous signposts marking regions where the universe is actively, yet gently, renewing itself, creating new generations of suns to illuminate the cosmic night. Their existence is a graceful, fleeting chapter in stellar evolution, a quiet testament to the continuous cycle of birth, growth, and gentle dispersal that shapes the stellar populations of the galaxy. Shifting our perspective from individual stars and clusters to the grander architecture of the cosmos, it becomes clear that stars are not evenly distributed throughout space. Instead, they exhibit a profound tendency to gather together, forming the immense luminous structures we call galaxies. These galaxies, in turn, are not scattered randomly, but arrange themselves into even larger, intricate patterns, forming what astronomers refer to as the cosmic web. This observation underscores a fundamental principle of cosmic organization. Gravity, acting over immense timescales, gently sculpts the raw material of the universe into these beautiful, hierarchical structures. From the smallest dwarf galaxies to the most majestic spirals and ellipticals, stars are the luminous building blocks, quietly congregating in their billions and trillions. Each galaxy is a distinct island of stars, gas, and dust, a self-contained celestial city. Yet each is also part of a larger, interconnected network. The clustering of stars into galaxies is a quiet, elegant consequence of the universe's initial conditions and the ceaseless pull of gravity, transforming a seemingly chaotic distribution of matter into an ordered, breathtaking tapestry of light. These vast cosmic structures, visible across billions of light years, are organization, a quiet, intricate weaving of light and matter into a grand, observable design, a beautiful, evolving architecture that spans the entirety of creation. Each galaxy, a silent beacon in the cosmic dark. Our own home, the Milky Way, is a prime example of such a magnificent galactic structure, a vast spiral island teeming with an almost unimaginable number of stars. Scientists estimate that the Milky Way contains anywhere from about 100 billion to 400 billion stars, each one a luminous furnace, quietly contributing to the galaxy's overall glow. This immense population includes a diverse array of stellar types, from the long-lived dim red dwarfs to the brilliant short-lived blue giants, and countless stars like our Sun, each following its own unique evolutionary path. These stars are arranged in a majestic spiral pattern, with luminous arms gently coiling around a central bulge, at the heart of which lies a supermassive black hole. The sheer number of stars within our galaxy is difficult to fully comprehend, representing a staggering collection of individual suns, each with its own story, its own potential planetary systems, and its own place in the grand galactic ballet. Despite this immense number, the distances between individual stars are so vast that our galaxy appears mostly empty, a quiet testament to the scale of interstellar space. The Milky Way is a dynamic and evolving system, its stars slowly orbiting the galactic center, creating a continuous, gentle flow of light and motion. It is our cosmic home, a vast, luminous tapestry woven from billions of individual suns, each a quiet, enduring light in the endless night, a constant source of wonder and discovery, inviting us to contemplate the sheer abundance of stellar existence. And when we extend our gaze even further, beyond the comforting confines of our own galaxy, to encompass the entirety of the observable universe, the numbers become truly mind-boggling. The total number of stars in this vast, visible cosmic expanse is estimated to be around 1 sextillion. To write that number out, it is a 1 followed by 21 zeros, 100 billion trillion stars. This astonishing figure represents an almost incomprehensible collection of luminous bodies, each a miniature universe of fusion and light, scattered across billions of galaxies and an even greater expanse of space. This estimate, however, applies only to the observable universe. the portion of the cosmos from which light has had sufficient time to reach us since the Big Bang. Beyond this cosmic horizon, the universe undoubtedly continues, stretching into regions that remain forever beyond our current perception, potentially containing an infinite number of additional stars and galaxies. The sheer scale of stellar existence within just the observable universe is a profound testament to the universe's boundless capacity for creation, a quiet, continuous process of igniting and sustaining countless luminous points of light. Each one of these sextillion stars contributes to the overall radiance of the cosmos, a collective glow that illuminates the vast darkness, a silent, countless chorus of celestial fires. This immense, uncountable multitude of stars paints a picture of a universe that is rich, vibrant, and filled with an almost infinite array of wonders. Each star, a quiet, enduring beacon in the grand unfolding narrative of cosmic existence, a testament to the profound abundance of light in the universe. As we gently close our exploration of stars, contemplating the 1 sextillion luminous beacons scattered across the observable cosmos, we are left with a quiet sense of the universe's infinite wonder and its profound, gentle rhythm. Imagine each star, a distant ember, a silent heart beating across the eons, contributing its soft glow to the cosmic tapestry. Feel the quiet drift through nebulae where new suns are slowly forming, or the serene, enduring dance of ancient galaxies. The universe is a place of ceaseless motion, yet also of profound stillness, holding both the fiery birth of stars and the long, slow fade into cosmic twilight. It is a space where light travels for billions of years, carrying ancient stories, and where even the vacuum hums with unseen quantum whispers. May this journey through the quiet wonders of the stars allow your own thoughts to soften, your breath to deepen, and your body to find a gentle rest. May your dreams tonight be as vast and peaceful as the cosmos itself, filled with the quiet beauty of distant starlight. Sleep gently now, knowing you are a part of this magnificent silent dance.